Okay, good evening. Good evening. Let's get started. Can you hear me? Can you hear me? Yeah, thank you. Good evening, everyone. Okay, so yesterday we have seen uh, DC analysis of the BJT. We have checked the region of operation, right? And I mentioned that if a transistor is properly connected, where the lower part is connected to the ground or the negative terminal, negative supply, and you have a positive VCC, then as you go up, the voltages should be in increasing order, right? So that's by logic, any circuit would behave like that. So it's your duty to see whether the BJT is on or not only by looking at one junction, which is the base to emitter junction. If the base to emitter junction is on, there is no need for you to worry. Even if there are 5 transistors, yesterday we have seen, we were just checking the base to emitter junction if it is on. But once the problem is over, as you go up, if the voltages are in increasing order, then the other collector base junction is what bias? Reverse bias, is it not? Okay, so what is the first problem that we have taken yesterday? This is the first problem. And you would have realized that this BJT analysis is no different from the simple diode analysis, right? So though the BJT has 2 junctions, it's as if you're analyzing it as if there is only one diode, is it not? So this is the diode. So we felt that the 4 minus 0.7 here is going to be 3.3 volt, and 3.3 by 3.3K, that is 1 milliampere. And the same 1 milliampere, almost 0.99 milliampere flows here, I see, is approximately 1 milliampere. Now, what happens if I change the load, right? If I change the load, suppose my load varies from 1K to 4.7K. 1K to 4.7K, as long as the emitter is at 3.3, the current will always remain at what? 1 milliampere, right? So that means what? A BJT is behaving as a constant current source. Is behaving as a constant current source. When you bias at an operating point of 1 milliampere, you keep on changing the load, the current is not going to change. So if my 4.7K is treated as the collector load, this is the RC load, right? The collector load, then though you change that 1K to 4.7K, your current is always 1 milli. Why is it 1 milli? Because the emitter is at 3.3. So now, during the next topic, biasing, please carefully observe where you are fixing the base potential and at what voltage you're fixing the emitter potential. Because the base potential, emitter potential, and the emitter resistor is a wonderful resistor. I mean, this resistor, as long as this resistor is there, the current is going to be independent of what? The load. You get a freedom from beta dependency. So whether beta is 100 or 200 or 300, this IC is almost going to be 1 milliampere. So even if you change the load, your IC is almost going to be 1 milliampere. So I was mentioning that this analysis is like the diode analysis, right? So what happens if you have a diode with an anode of 4 volt? An anode of 4 volt, the cathode is going to be 3.3. Am I right? 3.3. This is 3.3 volt. Because there is a drop of 0.7 volts. There's a drop of 0.7. If this is 3.3K, this current is going to be 1 milliampere. So just tell me how different is the BJT analysis with the diode? It's one and the same. But the only difference is this current has to come from the supply. It has to come from the supply, VCC or whatever, 10 volt. So this current is almost going to be 1 milliampere. So now even if you change the load here, as long as the BJT is in active region, if you maintain BJT in active region with a certain VC, is a certain amount of VC, right? At least greater than some value, greater than 0.2, is it not 0.5, 1, 2, 3, doesn't matter. As long as your collector is greater than the emitter, then even if you change the load, your operating current is going to remain constant. So that means BJT here is a constant current source, constant current source. Why is it constant current source? Why is it behaving like a constant current source? So this circuit is, do you remember in op amp I told you, I want a current source of 1 milliampere and my load is changing from say 1K to 5K, right? 1K, so here I wrote 4.7, okay, some value, don't matter, right? My load is changing from 1K to 4.7K, but even if you change the load, the current should remain constant. So such a current source is this circuit. This is such a current source. So BJT is acting like a constant current source, right? And beta 100, beta 200, beta 300, doesn't matter. Your IC is almost 1 milliampere. So this is the first problem we started yesterday, right? So I'm going to repeat this problem again and again. 4 volt, 3.3, 1 milliampere, there's also 1 milli. That's it. Now you change the load. When you change the load, your VC will change. Your VC will change, but your IC will always remain constant. Your IC is almost going to remain constant. Okay. So this is where we stopped, and we have seen the NPN transistor analysis and the PNP transistor analysis, right, of calculating the voltages and currents at the different nodes and branches, right? Okay. So we'll do some more. Find this voltage V1, V2, and V1, I1, I2, I3, I4, V1, V2, I1, I2, I3, I4, and VB on equal to 0.7 volts. You can take beta large. What do you mean by beta large? Your collector current and emitter current both are same. Okay. So let's solve. Now, the base terminal is connected to ground, so your VB, the base voltage, is at 0, right? So this is grounded. Grounded. Now you can see that the emitter node is connected to -20, right? If the anode is at ground and cathode is at -20, so that means what? The diode is what? Bias forward, right? So the base is at 0 volts. Then what is VE? VE is going to be V1. VE is going to be V1. The emitter voltage is nothing but V1. But we all know that VBE is equal to VB minus VE is 0.7. VB equal to VB minus VE is 0.7, which means that the base is at 0, V1 is at 0.7, so your V1 is going to be minus 0.7 volt. Your V1 is going to be minus 0.7, right? So last class, I told you that if you come down, you have to subtract, right? So there's 0 here. If you come down, it is 0 minus 0.7. It is going to be minus 0.7 is V1. Then what is I1? What is I1? It is V1 minus 0. It's V1 minus 0 by 1K. It is minus 0.7 by 1K. It is minus 0.7 milliampere. It is going to be minus 0.7 milliampere is I1, right? Now, what about I2 now? You can apply KCL. You can apply KCL. Entering current equal to leaving current. You can you see I2 here? This is entering. There are two currents leaving. I2 equal to 2 milliampere plus I1. I2 equal to 2 milliampere plus I1. But what is I1? It is 2 milliampere. I1 is minus 0.7 milli. This is going to be 1.3 milliampere. It is going to be 1.3 milliampere. So the current entering here is equal to the current leaving is equal to the current leaving. So your I2 is 2 milliampere plus I1, but I1 is minus 0.7 milli. That means it is 1.3 milliampere. That is 1.3 milliampere is I2. But I2 and I3 are same. But I2 and I3 are same because beta is large. I3 equal to I2. We know that IC is equal to IE if beta is large. If beta is large. So 3, this is the fourth one, right? I3. So I1 is known, V1 is known, I2 is known, I3 is known, right? Now what is I4? What is I4? What is I4? You have KCL here again. 6 milliampere is entering current and 2 leaving currents are there, right? So for fifth one, KCL is entering current. Entering current is 6 milliampere. Entering current is 6 milliampere equal to leaving currents I3 plus I4. I3 plus I4. So let's substitute now. I3 is already at 1.3 milliampere. Therefore, I4 is 6 milliampere minus I3. It is 6 milliampere minus 1.3 milliampere. So that is going to be 4.7 milliampere. It's going to be 4.7 milliampere is I4. And then finally, what do we have? We have V2. What is V2? by Ohm's law, V2 minus 0 by 1K is I4. Or by Ohm's law, what is V2? V2 equal to I4 into the resistor is 1K. The resistor is 1K, it is 4.7 milli into 1K. That is going to be 4.7 volts. It is going to be 4.7 volts. So let me check. V1 is at minus 0.7. I1 is minus 0.7 by 1K minus 0.7 milli. I2 is going to be 2 minus 0.7. That's 1.3. So you have 1.3 here. So there's 1.3 and 6 milliamperes. So this should be, I4 should be 4.7. So it's 4.7, right? Okay. Now tell me, is your collector greater than the emitter? Is VC greater than VE? That means is V2 greater than V1? How much is V2? 4.7. V1 is minus 0.7. True. True. Therefore, BJT is in active region. Therefore, BJT is in active region. So the procedure remains same. VE, IE, IE and IC both are same, and then VC, right? Never forget VE, IE, IC, VC. Find V naught if Vn equal to 4 volt, Vn equal to minus 4 volt. Find V naught if Vn equal to 4 volt and Vn equal to minus 4 volt. Okay. So as usual, this is an NPN transistor. Am I right? NPN. So here you have a diode. But this is a PNP. PNP. The diode is like this, right? So it's something like you have a diode here, you have a diode here, and here you're applying V. I think for this circuit, we have also drawn the transfer characteristics. If you remember, for this circuit, so we have two diodes here, the NPN diode and the PNP diode, right? QN and QP. So this is QN and QP. Now, out of the two diodes, which one is going to get on for positive voltage and which one is going to get on for negative voltage, right? Who is getting on for positive and who is getting on for negative, right? By seeing this, we can say that cathode is connected to ground, anode at Vin. So if my Vin is positive 4 volt, if my Vin is 4 volt, then QN is on and QP is off. QN is on and QP is off. So if QN is on and QP is off, then you have given the drop here is going to be 0.7 and you have given 4 volt here. So how much voltage will the resistor have? Right, so this V0 is going to be 4 minus 0.7. It is 3.3. This 3 point. Of course, this is our first problem, right? If I give 4 and the emitter node, if you take the output at emitter node, it is going to be one diode drop below, right? So it's going to be 3.3 volt. But what happens if I give a negative voltage? If I give a negative voltage B, Vin is going to be minus 4 volt. Minus 4. Right? So if you want, you can reverse the polarity and write 4. Right? Doesn't matter. The drop here is 0.7. Right? This is V0. You can apply KVL also if you want. Right? So you can say minus V0 plus 0.7 minus 4 equal to 0. So your V0 is going to be minus 3.3. So what is our answer now? If my Vn is 4 volt, my V0 is 3.3. If my Vn is minus 4 volt, my V0 is going to be minus 3.3. So how much is the drop between Vn and V0? There is a 0.7 volts drop between Vn and V0. Are you getting? So the same thing here. If my Vn is, so for Vn 4 volt, this is the transistor. So you're going 4 and Qn on and QP off. Qn is on and QP is off. So there is a drop of 0.7. So here you're going to get 3.3 volt. All right, 4 minus 0.7. So similarly, when Vn is minus 4 volt, here there is a drop of 0.7, right? This is V0. So what is 0.7 here? 0.7 is equal to V0 minus V. This is Vn. V0 minus V. The difference V0 minus Vn is 0.7. So if you substitute Vn equal to minus 4, right? then your V naught is going to be minus 3 point, right? In the previous example, what is the current source here? What is the current? This could be another BJT circuit. Are you getting? This could be another BJT circuit. The 2 milliampere current source, it could be another BJT circuit, right? So which is operating because of this plus 20 and minus 20. And is the BJT in active region or not? Is the BJT in active region? Because who sends the current to 1K? Is only the 10 volt supply, right? Is only the 10 volt supply is going to send the current to the load, right? As long as VC is positive. What is VCQN? VCQN is how much? 10 minus 3.3. It is 6.7 volts. That means BJT in active. BJT in active. Are you getting? Similarly, you can check for QP also. So there's minus 10 here. VEC. VEC QP. So what is V naught? The V naught here is minus 3.3, minus 3.3, minus of minus 10. It is again going to be 6.7 volts, right? So as you go up, the voltages are in what order? Increasing order. So the BJT in active region. BJT is in active region. Now, suppose if the load RC resistor in the first case, suppose this is the case, right? What happens if this 4.7K is replaced with a capacitor? Do you remember the Miller integrator we have discussed? So what happens if a constant current of 1 milliampere flows through the capacitor? Then the capacitor will charge in a linear fashion. Will charge in a linear fashion. So you're going to get a ramp generator. Are you getting, right? So the capacitor is not going to charge in exponential. It is going to charge linearly. if the current is constant. And I told you BJT is what source here? Constant current source. So if it is constant current source, what if I replace this resistor with a capacitor? Of course, I didn't replace, the examiner has replaced, right? The examiner has replaced it. A bit. Find is the find IC at t equal to 0 plus. Find IC at t equal to 0 plus. B. Find VC. Find VC at t equal to 2 milliseconds. C. Find time t. Find time t for the transistor to enter in saturation. To enter in saturation, your VC sat is going to be 0.2 volts. Is going to be 0.2 volts. Please never forget the rule. What is the rule? VE, IE, IC, VC. VE, IE, IC, VC. That's a standard rule, right? Of course, as long as there is an emitter resistor, as long as you find an emitter resistor, all it's much comfortable, right? You can very easily solve the problem without even having beta, right? Beta 100, beta 200, your answers are almost going to be same. So for this problem, you can take beta large, beta as large, right? Okay, so let's solve the problem. What is the first step? The first step is V, 1.7 volts, V. What is V? 1.7 minus 0.7 is going to be 1 volt. Is going to be 1 volt. Now here you have 1K. So what is IE? IE is approximately IC, which is 1 by 1K, that is 1 milliampere. It is 1 milliampere, and the same 1 milliampere is flowing through the capacitor. Is flowing through the capacitor. So if when the switch is closed, the capacitor voltage was 0. But the moment the switch is open, now there is a chance for the capacitor to charge, right? Previously, when the switch is closed, where is the current flowing now? The IC. If the switch was closed, all that current IC was flowing like this. This was IC. When this is IC, because current will always choose a low resistance path, right? So the capacitor is being bypassed by the switch. The capacitor is being bypassed by the switch. So the current is choosing a low resistance path. The capacitor was not charging, right? But surprisingly, once you open the switch, the IC is now flowing in the capacitor of 1 milliampere, right? So IC at t equal to 0 plus is 1 milliampere. 1 milliampere. This is A bit. What is B bit? B bit is, for knowing B bit, you should know the relationship between voltage and current in a capacitor. VC is 1 by C integral IDT. Am I right? So this is a formula for voltage across the capacitor. If the current is constant, 1 milliampere, I can remove it outside the integral. It is I by C of t. So it is 1 milliampere by 1 microfarad into time. How much is the time I have given? I said roughly 2 milliseconds, right? 2 milliseconds. So that means your VC is going to be 2 volts. Is going to be 2 volts. So because the numbers are very, very simple numbers I've given. Generally, I give simple numbers, right? 1 microfarad, 1 kilo ohm, like that. The current is 1 milliampere. So after 1 millisecond, it's charging to 1 volt. After 2 millisecond, it is charging to 2 volt, right? After 3 millisecond, it will charge to 3 volt. After 5 millisecond, it will charge to 5 volt. After 6 millisecond, it will charge to 6 volt. But how long does it go? How long does it go? It keeps going until the capacitor, until the transistor saturates, right? Until the transistor saturates. And because when VC is increasing, your VC is decreasing. See here, what is VC at this point? Your collector to emitter voltage. Your VC is this, right? So this is your VC, collector to emitter voltage. So your emitter is already at 1 volt. VC is VC minus V, right? VC minus V. VC is nothing but 10 minus, oh, this VC and the collector are misleading. So can I say V cap, right? V cap. 10 minus V cap minus V. So it is 8 minus 1, it is 7. So when you please see this equation, when V cap is 2 volt, when V cap is 2 volt, your VC is 7. When V cap is 3 volt, your VC will be 3 volt, your VC will be 6. So as the V cap increases, as a capacitor voltage, V cap here increases here, V cap, right? So V cap means V capacitor. VC means V collector, okay? I mean, just to differentiate, otherwise, yeah. V cap. So as the capacitor voltage increases, your VC will decrease. But when will it stop? When will it stop? To stop, this potential should reach 0.2. This potential should reach 0.2. And here there is 1.7 volts. If there's 1.7, there is 1 volt here. Yesterday I told you, if you go up, what will you do? If you go up, you will have to add. So it is 1 plus 0.2. It is going to be 1.2 volt. It is going to be 1.2. Now you tell me, what is the maximum voltage across the capacitor? What is the maximum voltage across the capacitor? V cap. V cap maximum is going to be 10 minus 1.2, it is 8.8 volt. 8.8. Therefore, 8.8 equal to I by C of t. Am I right? VC equal to I by C of t. 8.8 equal to 1 milli by 1 micro into time. So this is going to be 8.8 millisecond. 8.8 milliseconds. So let me repeat this here. See here, the numbers are very, very simple numbers are given, 1 kilo ohm, 1 microfarad, just for your better understanding, right? So if this is 1.7, this is going to be 1 volt here. Can you see the dot here, 1 volt? Then the current is 1 milliampere. With 1 milliampere, the capacitor is charging. At what rate it is charging? After 1 millisecond, 1 volt, 2 millisecond, 2 volt, 3 millisecond, 3 volt. What happens after 8.8 millisecond? After 8.8 millisecond, this capacitor will charge to 8.8 volt. So what is 10 minus 8.8? The collector, 10 minus 8.8 is going to be 1.2. But when this is 1.2 and the emitter is at 1, when the emitter is at 1 and the collector is at 1.2, how much voltage the collector and emitter has converged, right? As a capacitor is charging, the collector and emitter, slowly it is converging, right? So it has come to 0.2 after 8.8 millisecond, the capacitor the transistor has now entered into what region? Saturation. It has now entered into saturation, right? Now, all of you, what happens after that? What happens after that? After that, you will still have 1 milliampere here. You will still have 1 milliampere, but the capacitor has charged to the maximum. So the extra current is going to sink through the base region, right? So the base region, IB is going to be greater than IC by beta because the capacitor has gone to its maximum value. So capacitor cannot charge more than that. Are you getting? So even if there is a slight discharge in the capacitor to the resistor here, right? So in case, then if the value gets slightly less than 8.8 volt, again, it is going to charge. So maybe it's like, I mean, if you have a leaky capacitor and it is discharging, so the transistor will slowly come to the active region and then it might go to saturation. So we don't know, right? But to solve the gate problem, find the time t for which the transistor enters into saturation. After what time the transistor will enter into saturation? After the collector touches 1.2. When will the collector touch 1.2? So that your VC is 0.2 after when the capacitor has charged to 8.8, because 10 minus 8.8 is 1.2. Are you getting right? Fine. After 8.8 millisecond, the capacitor will enter into saturation. But please don't forget the procedure here. What is my first step? My first step is this. My second step is this. Am I right? And then my third step is this. So I came to know that the capacitor is charged to 8.8. Then my fourth step is the formula. What is the formula for the capacitor? The formula, let me write here. The capacitor will obey a formula. Vc equal to 1 by C integral IDT, which is equal to I by C of t. Never forget this formula for capacitor. Vc is 1 by C integral IDT, which is equal to I by C of t. So when is it I by C of t? Only when the current is constant. If the current is constant, then the capacitor is going to charge in a linear fashion. It's going to charge in a linear fashion. So your beta is going to fall down, right, terribly, because all the emitter current is now going to sink through what region? Base region, after it has entered into saturation. After it has entered into saturation, right? Okay. So this is a gate problem. I don't remember the numbers. It's difficult to remember the numbers. We will take the same one. Huh? So some random numbers, so don't worry, right? Just, yeah, I don't remember. So this is a gate problem. A bit is find the capacitor current, I cap, right? I cap at t equal to 0 plus. 0 plus. Find the time t for which the transistor enters saturation. See, VC sat, I think in this gate problem, VC sat is 0. The examiner has given 0. Of course, I'm taking 0.2, right? I'm framing the question, so it is my liberty. So let's take 0.2 for this problem. But if you solve a similar gate problem, I don't remember the values. So there in that gate problem, VC sat is given 0. If the examiner gives 0, take 0. If he gives 0.1, take 0.1. If he gives 0.2, take 0.2, right? He will give you. So you don't have to worry. Okay, so let's solve it. So what is the procedure? Don't forget VE, IE, IC, VC, right? This ground, so what is VE? VE is minus 0.7, am I right? There's a drop of 0.7 here. VE is going to be minus 0.7, right? And here you have a resistor, minus 5 volt. So VB VB equal to 0.7, which means VB minus VE is 0.7, which means VB is 0 and your VE is going to be minus 0.7, right? So if you come down, you should always subtract. From 0, you're coming down, so it's going to be minus 0.7. Then what is IE? IE and IC same, right? Because beta is large in the problem. Beta is large. So IC is approximately IE equal to VE minus of minus 5 by 4.7K. So it is going to be minus 0.7 plus 5 by 4.7K. It is 1 milliampere. It is 1 milliampere. Now tell me, I have I cap here. I have I cap and I have a current source here. Current source, right? So this current source is how much? 0.5 milli. And this IC is 1 milliampere. This IC is 1 milliampere. Right? So what is I cap? I cap equal to entering currents is equal to leaving currents. KCL. I cap plus 0.5 is going to be 1 milliampere. Therefore, I cap is going to be 0.5 milli. So unlike the previous problem, what happened here, there's only one, the current through 1K is 1 milli and the current through capacitor is also 1 milli. But in this gate problem, what the examiner did, an extra 0.5 milli is injected from here. So that means the current flowing through the capacitor is not 1 milli, it is another 0.5, because 0.5 plus 0.5 is going to be 1. Are you getting? So it is 0.5 plus 0.5 only is going to be 1. So if IC is 1 milli, then your I cap is going to be 0.5 milli. And there is a 1 microfarad capacitor here, right? So T equal to 0 plus, your capacitor is going to be 0.5 milliampere. Otherwise, when the switch is closed, this 0.5 milli is going through the switch when the switch was closed. Once the switch is open, naturally, there's an extra 0.5 milliampere flowing through the capacitor, right? So 0.5 milli plus 0.5 is 1. Now, what is B bit? When will the transistor enter into saturation? Tell me. This is ground. This is minus 0.7. You have 0.2 here, 0.2. What is this voltage? Minus 0.7 plus 0.2. Minus 0.7 plus 0.2 is going to be minus 0.5. Minus 0.5. And what is the capacitor voltage? This is minus 0.5. You have a 10 volt there, 10 volt. So this is 10. What is my V cap? V cap. And we know this current is only 0.5 milli because an extra current of 0.5 milli is going to come here, right? So how much time does it take for the capacitor for the transistor to enter into saturation? For the transistor to enter into saturation, what should be your V cap? V cap equal to 10 minus of minus 0.5. That is going to be 10.5. 10.5. So if your capacitor reaches 10.5, what is 10 minus 10.5? What is 10 minus 10.5? So if this is 10, if the capacitor has reached 10.5, what will happen? 10 minus 10.5 is going to be minus 0.5. So if this is minus 0.5, then your transistor has entered into what region? Saturation, right? Okay, so what is the formula for capacitor? I by C of t equal to 10.5. I is 0.5 milli by 1 micro time is 10.5. So previously for 10.5 volt, it was 10.5 millisecond because the current is 1 milli. Here the current is 0.5 milli. So what is 10.5 into 2? That's going to be 21 millisecond. So the time taken by the capacitor is going to be how much? 21 millisecond. So what is minus 0.7 minus of minus 5? Minus 0.7 minus of minus 5 is going to be 4.3, right? Oh my God, it's 4.3. Please change this to 4.3. My mathematics. Please change the question to 4.3, please. 4.3K. Don't put 4.7 because my number 1 milliampere is not matching here, right? Please change the question. I stand corrected here. 4.3. 4.3. Please change the resistor to 4.3. 4.3. Right? So 5 minus 0.7 is 4.3. 4.3 by 4.3K. Okay. Now it's fine. Minus 0.7 minus of minus 5 is 4.3. 4.3K you have to put, right? Okay. So everything is fine now. So a similar gate problem you can also solve, right? Okay, so let me repeat this once again. So what is the procedure? VE, IE, IC, VC. So the first step is VE. So this voltage is going to be minus 0.7. The current is going to be 1 milliampere. So this current is 1 milli. When this is 1 milli, already there is a 0.5 milliampere flowing here. So this current has to be 0.5 milli because 0.5 plus 0.5 is going to be 1, right? 0.5 plus 0.5 is going to be 1. Now, this capacitor is 1 microfarad, right? 1 microfarad capacitor. So after what time will the capacitor, will a transistor enter into saturation? So A bit is over. A bit is 0.5 milliampere because this one, this is 0.5. Okay. B bit is when will the transistor enter into saturation? For that, we should know the collector voltage here. To know the collector voltage, I have taken 0.2 volts here. I have taken how much? 0.2 volts. So we'll do it orally here. If this is 0.2, this is ground. What is this voltage? This voltage is minus 0.7. You have 0.2 here. So this is going to be minus 0.5. So 10 minus of minus 0.5 is 10.5. So 10.5 volt if the capacitor charges. But with what current? The current is not 1 milli, it's only 0.5. So remember, 0.5 milliampere current, 10.5 volt. So 21 millisecond, 10.5 into 2, I by C of t. After 21 millisecond, is going to enter into saturation, right? Now remember, in order to calculate the base current, whether it is in active or saturation or cutoff, wherever it is, please follow Kirchhoff's law. What is Kirchhoff's law? The current entering is equal to current leaving. At any instant of time, entering current is equal to leaving. That's it. Are you getting right? Entering is leaving. Entering is leaving. Who is leaving current in a NPN transistor? IE. What are entering currents? IC plus IE. Even if the transistor is in saturation or active, Kirchhoff's law will always be satisfied, right? The currents entering equal to current leaving. But please don't use IC equal to beta IB formula for saturation. Device formulas you should not use. General formula like algebraic sum of voltage in a loop is 0, KVL, entering current, leaving current. You can use them in any region, cutoff, active, saturation. There is no violation. You should not violate Kirchhoff's law. Entering, leaving is always valid, right? Okay. Yeah. So I was mentioning that if you have a the transistor analysis and the BJT analysis both look same, right? The transistor analysis and the diode analysis both look same. But what happens if multiple diodes are tied at a common point? If multiple diodes are tied at a common point, suppose two diodes are tied at a common point, right? Then which diode is going to get on? Which diode is going to get on? I told you that diode that experiences more potential difference is going to switch on. Do you remember this? Yes or no? Suppose I have given here 3 volt and here 0 volt, 0 volt. And this is some voltage here, say minus 10, right? This is say 10K. What is your current I? Out of the two diodes D1 and D2, which diode is going to get on? Suppose this node is X, right? 3 minus X, 0 minus X. Out which diode is going to get on? Naturally D1, right? Naturally D1 is going to get on. When D1 is on, what is 3 minus 0.7? You're going to get 2.3 here, 2.3. And this D2 is going to get off. D1 is going to get on. Do you remember this, right? We have done diode problems where multiple diodes are tied at a common point. The diode that experiences more potential difference is going to switch on, Then the other diode is automatically going to get off. Am I right? Yeah. Now, why not use the same technique here, right? I have a diode that is given 3 volt. And the cathode here is tied at a common point now, and the other one is given 0. And the cathodes are given to a resistor minus 10. And whatever answer that you get here is the same answer here. Because what is I in this case is going to be 2.3 minus of minus 10 by 10K. So it's going to be 12.3 by 10K is going to be 1.23 milliamp. So the answer here, of course, we are going to solve this, but the answer here and the answer here both are same. The effort that you put for a simple diode is the same effort that you put for circuits like this. And of course, your current is never going to depend on the load, so it doesn't matter, right? So you can take some load resistance values here. So let this be IC1 and IC2. Find IC1, IC2, and I if beta is large. just tell me if the 3 I change to -3, what will happen? If this 3 I change it to -3, what is going to happen? Naturally, D2 is going to get on, but D1 is going to get off. Am I right? D2 is going to get on and D1 is going to get off. So the same problem I'm repeating here. I'm giving -3 to a diode and the other one is 0. So this time, is the Q1 diode on or Q2 diode on? You have to see. Okay. Now, what happens if both are given 3? What happens if both are given 3? Do you remember the diode problem we have done? 3 volt, 3 volt, 3 volt. All the diodes, we use some technical word for that. Do you remember? What did we say? We call that as what sharing? What sharing is that? Load sharing, right? That was called load sharing. So the both the diodes are going to get on and the current that is flowing here, I, is going to get distributed into 2 equal parts. Is going to distribute into 2 equal parts. Do you remember this? Yes or no? So the effort that you put on a simple circuit like this, right, is the same effort here also, right? So what if I connect both diodes to 3? I'm taking 2 diodes and I'm giving them to 3 here or 0 here and 0 here. And doesn't matter because there is a negative voltage here. Fine. IC1, IC2, and your I0. So simple diode circuits. The same answer you're going to get. The same answer you're going to get uh, even in BJT circuits, right? As compared with the diode. Okay, so let's solve it. So I have the NPN diode here and the PNP and another NPN diode, right? Two NPN diodes are there. But one end anode is connected to 3, the other end is at 0, and there is a common voltage here V, right? There's a common voltage here V. Here. Now tell me 3 minus V and 0 minus V. Out of these two, which one is going to get on? Who experiences more potential difference? Q1. So Q1 base to emitter junction experiences more potential difference. More potential difference, right? So Q1 on and Q2 off. If Q1 is on, what is the voltage here? 3 minus 0.7. What is 3 minus 0.7? It's 2.3, right? So this is going to be 2.3. Your VE is going to be 3 minus 0.7. It is 2.3. With VE of 2.3 here, see here, VE is 2.3, cathode is 2.3, anode is at ground, so naturally Q2 is going to get off. Now, what is I? I or I not? I is going to be how much? VE minus of minus 10 by 10K. It is 2.3 plus 10, 12.3, 1.23 milliampere. 1.23. Now, how is this current steered now? This current is steered through Q1, right? Because according to Kirchhoff's law, here we have IE1, here we have IE2. So tell me, what is I? I is equal to IE1 plus IE2. IE2. This is approximately IC1 plus IC2, because if beta is large, your IE is approximately IC. So this IC1 plus IC2 in all these type of problems, IC1 plus IC2 is going to be the total I here. Is going to be the total I. IC1 plus IC2 is going to be the total I. Okay. But what is IC2? What is IC2? IC2. What is IC2 here? What is IC2? IC2 is 0. But IC2 equal to 0 because Q2 is off. Therefore, I equal to IC1 equal to 1.23 milliampere. So this is a final answer. Your I and IC1 both are same and your IC2 is 0. That means all this current is steered through Q1, right? So this is a current flowing. This is a current flowing and your IC2 is 0, right? Of course, this is expected even in a diode problems, right? If two diodes are tied at a common point, only one diode is going to get on, the other one is going to get off. Am I right? The other one is going to get off. So on the same token, tell me what is the answer here? What is the answer here in the second problem? Okay, so what about this problem? This problem, here we have a diode. Here again there is a diode. All right, two diodes are there. So D1 is off and D2 is on. The voltage here is going to be minus 0.7. Then what is current I? I is going to be, so here there's 0.7 here. Here VE is minus 0.7. Then what is I naught or I? I naught equal to VE minus of minus 10 by 10K. It's going to be 10.7 by 10K. 1.07 milliampere. This is I naught. But I naught is same as IC2, right? Q1 is off. As Q1 is off. As Q1 is off, that means your IC1 is 0. But I naught equal to IC1 plus IC2. If IC1 is 0, what is IC2? IC2 is I naught equal to 1.07 milli. So your answers are this, right? The final answer is all this current here, I naught, is steered through which transistor? Is steered through the Q2 transistor this time. In the previous case, the IC1 is same as I naught. Now in this case, your IC2 is I naught. Your IC2 is I naught. But what happens if both diodes experience same potential difference? If both diodes experience same potential difference, ground and ground, this is going to be minus 0.7. This is I naught. And please mind you, what is each current here? I naught by 2 and I naught by 2. It is going to be I naught by 2 and I naught by 2. That is load sharing. That is load sharing. So let us do it now. What is V? Both the diodes are on. Both the diodes are on. Your VE is going to be minus 0.7. I naught is going to be minus 0.7 minus of minus 10 by 5K. All of you, what is 9.3 by 5K? I think yesterday in BJT problem, there was this 9.3 by 5K. You got some 1.86 milli, no? Is my memory okay? Just see, yesterday we have done a PNP transistor like 9.3 by 1K. By 5K, it's like 1.86 milli, something we got. Yeah, 1.86, okay. It's 1.86 milliampere, right? This is the number in yesterday's PNP transistor problem. Fine. I naught is 1.86 milli. Then what is IC1? IC1 plus IC2 is I naught. But IC1 equal to IC2. IC2. Therefore, IC1 equal to IC2 equal to I naught by 2. What is 1.86 by 2? 2 ones are 2, 2 nines are 0.93 milliampere. So this is the numbers, final answer. Yeah, yesterday I was telling you that we can convert NPN transistors into PNP and the PNP to NPN, but your answer is not going to change. Did I tell you that? Yeah. Suppose I want the same answers, the same answer of this problem. Just help me. How can I draw? How can I draw to get the same answer? But my transistor should be PNP. So I'll draw two PNP transistors here. Yeah, two PNP transistors. And let's see what connections we have to give one by one. Slowly we have to give, right? What is the easy connection in this circuit? Ground, right? Base is connected to ground. Base is connected to ground. So base is connected to ground. Base is connected to ground. All right? Yeah. And next, both emitters are shorted. Both emitters are shorted. Both emitters are shorted. Right? Okay. And you have given a resistor of 5 kilo ohm. You have given both emitters are shorted, and you have given a resistor of 5 kilo ohm. Okay. And what about collectors? Collectors have two resistors, two collectors are there, and there are two resistors, each of what value? 2K, 2K. Each of 2K, 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 2K. Right? So now all the connections are done. And when is BJT in active region? As you go up, the voltages should be in increasing order. So naturally, this side we will have to have a what is that supply plus 10, and this side we are going to have here minus 10, right? Minus 10. Minus 10. Well, you can short it. Minus 10. Okay. Let's see if we get the same answer here. I not. This guy is IC1 and this guy is IC2. Right. So find I naught, IC1 and IC2. So if the examiner gives you a PNP, you can simply convert it into an NPN. Your answer is not going to change, right? Okay, so let's see. Fine. First this is a diode. So you have a diode here. So what is your V? What is your V? Your V is directly a drop of how much? 0.7. Your V is 0.7. Then what is I naught? It is 10 minus VE by 5K. 10 minus 0.7 by 5K, you got 1.86 milliampere, right? And this current is split into two currents, IC1 and IC2. IC1 plus IC2 approximately is I naught if beta is large. Beta large means base current is neglected. So because both the diodes are on, both diodes have got 0.7, 0.7, they experience same potential difference. Your IC1 is going to be IC2 is going to be I naught by 2, which is 0.93 milliampere. Let's see, did we get the same answer here? Yeah, of course, right? Same thing. Zero 0.93, yeah, 0.93. Now, I told you, is my IC depending on the load? Is my IC depending on the load? No, is it not? So even if you have 1K, 2K, 3K, 4K, as long as the BJT is in what region? Active region, your IC is never going to depend on the load. So even if you have 1K, 2K, 2K, 3K, 3K, 5K, 6K, 7K like that. RCs are different. Your IC is still going to be the same. Your IC is still going to be the same. But this drama will continue only when the transistor is in what region? Active, right? When the transistor is in active region, it is like a constant current source. It is like a, but not a very good current source, because I told you, if load changes, then your VC will slightly change. If VC changes, then there is early effect, right? But all the DC parameters, when we are calculating, we are neglecting that early effect, and we are saying that my current is only dependent on VE. VB, VE, that is enough. The emitter potential and the emitter resistor. So my operating current, it is not going to depend on RC. It is going to depend on VB, VE, and RE. RE is the emitter resistor. RE stands for what? Emitter resistor. So it's going to depend, it's not going to depend on RC, right? But here we are not making that much mistake, even if it depends on VC, right? But in BJT AC analysis, definitely we are going to consider early effect and do, right? So right now, no problem. My V is fixed. My I naught is 0.93 milliampere. Okay. It's not going to depend on the load, however. Okay. So these are the different types of BJT problems to start with. Now, the current IC that is flowing, this IC current is called the operating point. It's called what point? Operating point. IC, comma VC, or rather VC, comma IC. The voltage in a BJT is VC and IC. So in the characteristics, of the BJT, this is VC and IC. So my operating point should remain fixed. As long as my IC is fixed here, even though there is a change in VC or the change in load, right, or the change in temperature or any other external factors, my AC parameters are predictable. So what happens if my IC is constant? If my IC is constant, after the biasing topic, we'll go for AC analysis. In AC analysis, you'll realize that the transconductance of the BJT, GM, and the R pi of the BJT and R naught, all these are interdependent on IC. So and from here, you can calculate AV, AI, RIN, R naught. So complete BJT analysis is interdependent on the operating point. If your operating point changes, then the dynamics will change, because this is not BJT analysis. Please, what we are doing is only DC analysis. With DC analysis, this is not BJT analysis. BJT analysis means signal analysis or AC analysis. And your AC analysis are dependent on the DC operating point. So this is something we have seen even in diode small signal analysis. Your AC analysis of a diode is dependent on your DC operating point. If the DC operating point changes its value, your AC parameter GM, R pi, R naught will change its value, and voltage gain is not predictable. Morning one voltage gain, afternoon another voltage gain, evening another voltage gain, because your operating point is dependent on temperature or load or any other factor. So what is the purpose of biasing, which is the next topic, is we have to see that this current 0.93 milliampere here should be constant. In the previous case, what is the current here? 1.07 milliampere IC1, and this 1.07 milliampere should be constant. In the previous problems, you can see IC that we have calculated in so many problems, right? So this I3 here is how much is I3? 1.3 milliampere. This should be constant. So in this circuit, the 3.3 milliampere should be constant. So in every BJT circuit, we have seen currents, or those currents should remain constant. That is the purpose of biasing, right? So let's go there, right? So yeah, please write down biasing a BJT. Biasing a BJT. So what we are doing here, same thing what we have done till now, but a little formally. a little formally. We will use terms like operating point and all. Till now, I said calculate IC, IC, IC. Now I'm saying calculate the operating current. That's the only difference, right? Biasing a BJT. So what is the purpose of biasing? The purpose of biasing is to switch on the BJT to work in active region such that the DC collector current, so what are the other names for DC collector? Yesterday in the doubt session, a girl was asking me, so what is this DC collector current? What are the other names for DC collector current? You can call it quiescent current. You can call the DC collector current as what? Quiescent current, or static current, or what are the other names for this? Or zero signal current. So these are all synonyms for this, right? So you can call it as a DC collector current, or quiescent current, or static current, or zero signal current. So that current, such that the DC collector current should remain constant, irrespective of variations in beta, temperature, and load variations, right? Beta, temperature, and load, right? So the purpose of biasing is to switch on the BJT to work in what region? Active region, such that the DC collector current, or the quiescent current, the zero signal current, that current ICDC should remain. So this ICDC, the DC collector current, which is ICDC, should remain constant. It should be, you should nail it. You should say ICDC, stay here, right? Don't move. The value should not change. Because if that value is constant, I told you, your GM, R pi, R naught, AC parameters are interdependent on this. Then your voltage gain, current gain, input resistance, output resistance, all the AC parameters are under your control. They are predictable. Otherwise, BJT is very bizarre. It's very bizarre, highly nonlinear. So it's so difficult to tame this fellow, right? So biasing is the fundamental thing. It's an art. You have to first take a BJT and tame it in such a fashion that the current, you have to decide the current. The temperature should not decide. The manufacturer should not decide, right? The BJT. Tomorrow you remove a BJT, put another BJT with a different beta value. Your operating current should remain same. Your AC gain is always predictable, and the value should be constant, stable, right? The value should not keep on changing with beta, with the temperature, with load. What do you mean by variation of beta? Beta means, beta is a device parameter. Device parameter means, suppose if you go to the shop, the shopkeeper, right, and ask him, give me BC 147, he will give you. Give me BC 547, he will give you. But you just ask him, give me beta 100. That fellow will say, I don't know, beta kya hai? Huh? Then you have to, because he does not understand what is beta. He will put in front of you, 50 transistors and say, jo bhi beta chahiye, le lo. Because each transistor will have its own value of beta. He does not know. One transistor will have beta, because shopkeeper, he has no knowledge of electronics. He thinks that all transistors are same. But we know, because we know electronics, we know that one transistor will have beta 50, the other transistor will have beta 55, there's one transistor with beta 100, there's another transistor with beta 200, beta 250. So when you buy a transistor, you're actually not picking the same transistor, you're picking a different transistor. Even if you replace another transistor, in the place of beta 100, if you put beta 200, your operating current should remain constant. So beta means device. Beta means what? I am irrespective of variation of the device. So I remove a transistor and I put another transistor, my operating current should be same. What do you mean by temperature? Temperature is going to change your VB, is going to change your VB. I'll tell you, it's going to change by 2.5 millivolt for every 1 degree rise in temperature. So this is, you should have control over VB. This is, if temperature changes, who will change? VB changes. So you should create an equation of IC which is not dependent on VB. See here, any IC equation we have seen, it is dependent on VB. This is waste. You should see that your IC does not depend on VB. What is this load? Load means what? VC, early effect. Early effect. So one by one, we will see. Now, please remember, some biasing circuits will combat with beta dependency, right? So some biasing circuits will combat with early effect, but they still have a problem of temperature. Some biasing schemes are temperature, they will eliminate, beta they will eliminate, but they cannot eliminate early effect. So our main aim is to create a circuit which fights with beta variation, temperature variation, and the load variation. And finally, you should get a constant value of IC/DC. Are you getting? So the purpose of biasing is to nail that operating current, because in the next topic, when we go for AC analysis, our AC analysis is completely dependent on the DC operating point. So you have to fix IC/DC, right? So whatever we have done, the same thing we are going to continue now. Okay. But what is the first circuit we are going to see? The first circuit that I'm going to see is the worst circuit in electronics, right? So it's a worst circuit in electronics. The reason I'm introducing this circuit is to tell a student, don't use it. Never use the first circuit that I'm going to draw, because this is how you learn, right? So first you should take some worst things, right? This is what our parents will teach us. They will never tell what we should do, right? Every parent will never tell what we should do. He will only tell what we should not do, right? Don't do this, 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 don't do this. So when you don't do a set of things, then you're left with very few things to do, and automatically you're stable. You're stable, right? So that's the method we are trying to learn here, right? First, we are going to teach some worst circuits and say that don't design it. Then if you design in the other way around, so naturally you're going to be a good designer, right? So what is the worst circuit in electronics, which has all the problems of the world, right? That is called fixed bias. It is called fixed bias. Never use this circuit. It's only on paper. You have to learn this, but never ever try to use this, right? Fixed bias. Fixed bias. And personally, I like this circuit, right? So I like the circuit. I'll tell you why I like it. Because this is a very good way to start biasing. So it's like a child taking his first step, right? So when a child takes a first step and he staggers when he tries to walk, it's great to see, right? But is it a good walk? No, but it's a good way to start, right? So this is an excellent way to bias the BJT, right? It's an excellent way to start learning biasing. But if you ask me, is it a good circuit? No, this is the worst circuit in electronics, right? So what is IB here? What is IB? So this is VCC with respect to ground. If you want, you can apply KVL around the loop. So it's minus VCC plus IBRB plus VB equal to 0. So what is IB? IB equal to VCC minus VB by RB. VCC minus VB by R. So this is the worst equation anybody can expect, right? Till now, did I ever got IB equation? So many problems we have seen. Yes or no? Almost from yesterday, we have seen around 20, 25 problems, but not a single problem I got IB while the transistor is in active region, right? How was that possible? That was possible because I had a beautiful emitter resistor. If I have an emitter resistor, directly you go VE, IE, and IC. That's it. There is no question of IB. So what is the purpose of biasing? Is to fix the collector current. Can you see here? Is to fix the collector current. This worst circuit is fixing base current. So that your collector current is purely dependent on the device beta. IB is VCC constant, VB is almost 0.7 constant, RB constant. It has fixed your IB, right? That means it has fixed us. So we are in a fix now. Never use this circuit. What is IC? IC is beta times of IB. Never use this circuit. IC is beta times of IB. It is beta times of VCC minus VB by R. IC is VCC minus VB by R, right? So I told you what is beta? Beta is a device. What is beta? Beta is a device, right? When you go, it's like I have a transistor here. Say I'm having 5 transistors with me, right? I'm having 5 transistors with me. And this guy has got beta 50. Say this is beta 100. This is beta 105. This is beta 200. And this is beta 250. 1, 2, 3, 4, 5. 5 transistors I'm having in my shelf, right? Now, this BJT is gone. So when the BJT goes, how will you check the BJT? You just remove the BJT and put your multimeter in resistance mode and check the junctions here. Junctions are gone. Now what you will do? Previously, this BJT was beta 100. For example, this is beta 100. Now what you do? You open the shelf, draw, and you have 5 transistors with you, right? Beta 50, beta 100, beta 105, beta 200, beta 250. So we don't know what is when you see a transistor, when you see a person, do you know his name? It's like that. When you look at the BJT, you will not know what is the device beta, right? So randomly you pick a transistor. Suppose I picked a transistor, this one I picked from my shelf, and I connected it here. What will happen? Previously, when my operating current is 4 milliampere with this beta 100, now it will be beta 200, it's going to 8 milliampere, finished. Complete parameters of your amplifier have changed because this worst circuit is dependent on the device itself. So see, analog is not device, analog is the design perspective. The design should be so intact, so rock solid that even if you replace a transistor with another transistor, your operating currents and the gain, everything should be same. Everything should be same. So now if I remove beta 50, beta 100 with beta 200, finished. What happens if I replace it with beta 250? Still high, right? Beta 50, the current is going low. So please, so what should I write here? Note, beta is not a good transistor parameter. Beta is not a good transistor parameter. Beta depends on, and see, the good news is, even this beta 100 will not be constant. Beta 100 manufacturer will give you, that beta 100 will change also with temperature. Beta depends on temperature, frequency, manufacturer, process variation, right? Okay, so beta, the transistor that you are using was dependent on temperature, frequency, process, everything. It's changing its value. Now that transistor, you went for a replacement. Now the real story starts. Already this is a worst circuit. If you replace it with another beta, that transistor, we don't know who made it. Yes or no? So what is beta variation in the market? Beta varies from 50 to 250 for the different specimens of a given transistor type. Beta varies from 50 to 250 for the different specimens of a given any transistor that you buy in the market, BC147, 547, the shopkeeper does not know. He's got a bunch of transistors where each transistor will have a different value of beta, and the variation is where some transistors, the extremes I'm just telling you, the extremes are if he has 1,000 transistors with him, the least beta of a transistor will be 50 and the maximum beta which he is having is 250, right? So 250 to 50, randomly if you close your eyes and pick a transistor, right? So you apply your probability theory or whatever, do you think you will pick exactly beta 100? It's not possible. 100% your circuit parameter, the IC is going to change. This is the worst circuit in electronics. See, that is why I tell students, take it on a lighter side. If somebody asks you in an interview on what parameters beta will depend, right? I told you in my first class, whatever comes to your mind, you tell. Beta will change. Even if you cough also, beta will change. So beta is like a worst parameter. You have to do something in the design such that the current equation should not have beta, like how we have done 4, 3.3, 1 milliampere, 1. You should design like that. Never ever design a circuit without an emitter resistor. See, there is no emitter resistor. Your IB is fixed. Beta varies from 50 to 250 for the different specimens of a given transistor type. So what is the final statement I'm going to make? Any circuit that depends on a particular value of beta, value of beta is a worst circuit. That means in any circuit equation, if you get beta and it is dependent on that particular value, that means you're a bad designer. Never ever try to design a circuit which depends on a particular value of beta. Then how are we going to remove it? If you want to remove it, then you have to bias with which resistor? Emitter resistor. In all our problems, even that big problem we have done, no? Big problem. Emitter resistor. Without an emitter resistor, RE, you should never design a circuit. Because this resistor will give you freedom from beta dependency. You don't have to worry in any of the equations about beta. Directly VE, IE, IC, VC. VE, IE, IC, VC, right? Okay, so give me a KVL here. This is VCC with respect to ground. So what is KVL? Minus VCC plus IBRB plus VB plus IERE equal to 0. Equal to 0. Then how to eliminate your IB? What is the relation between IB and IE? IB and IE. Yesterday I've given you know. What is the relation between IB and IE? IE is beta plus 1 times of IB. Am I right? Or your IB is IE by beta plus 1. Am I right? Now you substitute 2 in 1. 2 in 1. Then what is IE? IE is simply, just tell me logically, what is the current here? It is potential difference by resistance, right? Potential difference. What is the potential difference there? VCC minus VB, the potential difference. What are the resistors in that loop? What are the resistors in that loop? One is RB, the other one is RE. So because it's emitter current RE and the base current is there, so I'm going to divide by 1 plus beta. Are you getting? So why I have to divide by 1? Because the actual current is IB while writing KVL. So I'm writing for IE. Or you substitute what is there. Substitute 2 in 1, you get this equation, right? But I'm just telling logically, I equal to V1 minus V2 by R, right? Ohm's law. By thinking Ohm's law, VCC minus VB by RE. In RE, there is IE, but in RB, there is IB. So I've divided that current by 1 plus the resistance by 1 plus beta. Okay. So this is IE. Or you can substitute 2 in 1. This is approximately ICDC. This is approximately ICDC. But see here, still there is beta dependency, right? Still there is beta dependency. But okay, as compared with the first circuit, this at least you have got this factor 1 plus beta in the denominator. So what happens if beta from 100, you change it to 200? This beta from 100, if you change it to 200, then this value will still get less. Yes or no? So if beta is large, this value will still get less. So please choose RE far greater than RB by 1 plus beta. If you choose RE far greater than RB by 1 plus beta, then your IC is approximately going to be VCC minus VB by R. VCC minus VB by R. Am I right? So somehow we were able to eliminate it, but still there is a slight dependency, but so far so good, right? As compared with the first circuit, the first one was worst. Directly the factor is multiplied by beta. You can see here, there is a multiplication factor. From here, somehow we were able to push that factor to the denominator, right? So your IC, which is IE, is VCC minus VB by R. See in 12F, did I make a mistake here? 12F, one of the student is in the comment section is writing VE minus of minus 10 by 10 point. Did I make a mistake here? What is VE here? Minus 0.7. It's correct only here. But where is the mistake? Minus 0.7. Oh, this is minus 0.7. If it is minus 0.7 minus of minus 10, this is going to be how much? What is this value? Minus 0.7 minus of minus 10. This is going to be 9.3. All right. So this is going to be 0.93 meter. Very good. I stand corrected. 0.93 meter. But in which problem I have done it correct? Minus here. Minus 0.7. This is okay. Did I make the same mistake here? This is 3 minus 0.7, 2.3, 2.3 plus 10, 12.3. Yeah, that's okay. Fine. See here, any textbook, this has this equation. When I look at this equation, I start thinking, will this circuit actually work? Will this circuit actually work? Because the inequality here, when you say RE much greater than RB by beta plus 1, I'm much worried about this equation. The reason is, by looking at this equation, indirectly, I'm neglecting the drop across RB. I'm neglecting the drop across RB if my RE is much greater than RB by beta plus 1. Now, what will happen if I neglect the drop across RB and the complete VCC appears at base? And the complete VCC appears at base. What will happen? Yesterday, what is the second problem we have done? First problem, we have given 4 volt. The BJT was in active region. When I increase the 4 volt here to 6 volts, what happened? 6 volts, the BJT entered into what region? Saturation. Am I right? So that's quite dangerous that you cannot increase the base potential here. So this inequality is dangerous. So I'll make a note here. Note. If RE is far greater than RB by beta plus 1, then the base potential increases. So BJT can enter into saturation. Can enter into saturation. Now, how to avoid this? How to avoid, right? To avoid decrease the base potential with a voltage divider. So, if you connect a voltage divider, then definitely you can decrease that base potential, right? So that is the voltage divider bias. Voltage divider bias. This is also called self bias. Self bias. So what happens if RE is far greater than RB by beta plus 1? See here, okay, all of you just see here. From the equation, can you build a circuit? Then it will be much clearer. No? So I got some equation. VCC minus VB by RE. VCC minus VB by RE is IC. What sort of circuit is this from this equation? Let me draw it here. So only this circuit will give you such an equation here, because what is the emitter voltage here? Emitter voltage, if this is VCC, this is going to be VCC minus VB. What is the emitter current IE, which is IC? VCC minus V. See, how can you bring the whole VCC here almost by choosing a larger value of Re, and Rb by beta plus 1 is much smaller, right? So it's difficult. I mean, even if this voltage increased from 4 volt to 6 volt, BJT entered into saturation. I think 4.76 volts yesterday's class, the EOS condition. What is EOS? The edge of saturation was 4.76. So I told you this potential should be less, it should decrease. You cannot choose Re far greater than Rb by beta plus 1. Am I right? So that is why what we have to do is, let us connect a voltage divider. Let us connect a voltage divider like this. Let us connect a voltage divider and calculate IC. Calculate IC. Okay, shall we take a break now? We'll take a break. When we come back, we will calculate the IC current in a self-bias circuit or a voltage divider bias. Okay, can you hear me? Can you hear me? Yeah. Now, why is it called self by self? What do you mean by self? Self-sufficient, right? Self-equipped, self-sufficient, self-bias. The word self means you don't need an separate voltage here, right? So we have given separately here 4 volt, right? In the first problem that we have done, instead of that, that 4 volt we are going to bring from a voltage divider. We are going to bring that from a voltage divider, right? By having a slightly larger R1 and a lesser R2, something like that, right? So you can have suppose if your VCC is a 10 volt, and your R1 can approximately be what, 6K, and R2 4K, something like that, right? For a beta large value. But beta is finite, we have to do it carefully. Now, how do I solve for IC? How do I solve for IC? What is the voltage at this node? At this node, it's VCC. So the voltage at this node is also VCC. Can you see the voltage at this node? So let me draw it like this. You have R1, R2. There is VCC at this point. There is VCC here. There is RE, RC, and VCC. All right. So it's the same VCC at this point and this point. Or VCC is a voltage at that point with respect to ground. All right. VCC is a voltage at that point. When you have plus VCC, the minus is connected to ground. So this is VCC. And the plus terminal of VCC is connected to R1. R1. And here you have R2. R2. And this is given to the BJT, RE, and you have RC here and VCC. So we can draw like this, right? So it's one and the same. It is VCC with respect to ground and R1 and R2. Now in my first class, I told you, how can I remove this? You can do source transformation also. What is source transformation? You'll have VCC by R1 as a current source, and then you can convert it into a voltage source, right? So let's have a source transformation, or you can have Thevenin, right? Your wish. So what is a source transformation for this? This is VCC, R1 and R2. This network is equivalent to a current source of VCC by R1 in parallel with R1. And here you have R2. All right. So this is R1 parallel with R2. R1 parallel with R2. What is R1 parallel with R2? It is R1 R2 by R1 plus R2. That is equal. Now, how can I convert the current source into a voltage source? The current multiplied by this value. So the voltage here is going to be VCC by R1 into R1 R2 by R1 plus R2. So your R1 gets cancelled. VCC R2 by R1 plus R2 in series with R1 parallel with R2. So this is by what transformation? Source transformation, because if you don't like the voltage divider, you can do like this, or you can directly apply the node method. So now I'm going to replace VCC R2 by R1 plus R2 in series with R1 parallel with R2, right? So this is the network here, right? So I'm going to replace this network with this network, and here there is a BJT. All right. So this equivalent is nothing but the Thevenin equivalent. We have already seen the V Thevenin value, the VOC here, VTH is going to be this value VTH, and the resistance RTH. What is RTH for this? The RTH here is going to be, you can short the voltage source, then R1 and R2 both are in parallel, right? That is okay. And you have VB here on, and there is IE. There is IE. So now you can give me a KVL. You can give me a KVL down the loop, minus to plus, minus VTH plus IB into RTH plus VB plus IR equal to 0. And to eliminate IB, IE is, or IB is IE by beta plus 1. Then if you substitute 2 in 1, what do you get? What do you get? Directly, without writing all these equations, directly how you can tell? VTH minus VB, V1 minus V2 by R1 plus R2. So you have to imagine that in that loop, there is only IE flowing. Imagine there is an IE flowing there. Then what will you write for IB? IB is nothing but IE by beta plus 1. So if you write, so you can directly write this as VTH minus VB by RE plus RTH by beta plus 1. RTH by beta plus 1. This is your IE. Is approximately ICDC. Is approximately ICDC. Okay. Now what value will you choose? You have to choose RE far greater than RTH by beta plus 1. Or what is RTH? R1 R2 by R1 plus R2 by beta plus 1. So if you choose this, then your IC or your IE is going to be VTH. VTH is VCC R2 by R1 plus R2 minus VB by RE. So this is the final equation we have got, right? And thank God the voltage divider VCC R2 by R1 plus R2. So before the break, we were worried if you directly give VCC to the base terminal, then the transistor can enter into saturation. But what is the base voltage here? It is approximately, if you neglect the IBRB drop, the base potential is VCC R2 by R1 plus R2. So thank God the base is at a lower potential. There is enough headroom for collector-based junction to get reverse bias. See, what happens if the base potential is less and your collector is at a larger potential? Then the collector-based junction should be reverse bias. So the BJT will be in active region, right? Okay, so finally your collector current is VCC R2 by R1 plus R2 minus VB by RE. So far so good. We have eliminated what dependency? Beta dependency, right? Still two more are there, maybe three more. This equation also I don't like. Why do I don't like this equation? Because there is VCC also here. So can I have a circuit current that is independent of VCC? Independent, I mean, power supply should be there, otherwise current will not flow. But in the equation, VCC should not be there. So what happens in the equation if there is no VCC? Then your amplifiers in your cell phone are like that. So the amplifiers in your cell phone, your battery keeps on draining. So imagine your battery in your cell phone is keeping on draining, right? It's getting less. But the performance of the cell phone should still be same. Why is the performance of the cell phone still same? Because the currents there in those current equations of the transistors inside your cell phone, there is no VCC there. So that there is the currents inside the transistor are constant. Even if your battery drains, the current should remain constant. So that is also we have to see, right? And VB, I told you, what is VB? VB is if temperature changes, VB will also change. If VB changes, your IC will also change. So we have to address the VB problem also, the temperature problem. And of course, I told you the last problem is the early effect. So how are we going to combat early effect? Your IC-DC should be independent of the variation in VCE. Because if VC changes, your VCB will also change. Okay. And I have to mention that when I was writing GATE exam, right, so there were theoretical questions also, right? So off late, we have seen only problems, mostly problems, right? But we used to have theory questions also. And the characteristics of RE resistor was very, very important when we were writing GATE exam. So let me mention that. What is the characteristic of an RE, right? What's the use of RE resistor, right? What is its characteristics? So what is the characteristic of RE, right? We have seen that RE gives freedom from beta dependency. So let me write that it gives stability of IC-DC independent of beta, right? It gives stability of IC-DC independent of beta, right? So there's no beta dependency if you use an emitter resistor RE. The second thing is RE gives thermal stability to the circuit. Thermal stability to the circuit. So I have to explain this, right? And the other benefit of RE is in AC analysis, I'll show you AC analysis. When you do AC analysis, you will realize that RE increases input resistance and decreases the voltage gain. RE increases input resistance as well as output resistance, right? So input resistance and output resistance. RE increases input resistance and output resistance. And why so many and? But you'll write but decreases the voltage gain. RE increases the input resistance and output resistance, but it decreases the voltage gain, right? So these are the benefits of having RE. See, just one resistor, see how much implication. That is why I tell you, without an emitter resistor, you should never design any circuit, right? So take this for granted. There should be an emitter resistor. Emitter resistor means something you should connect at the emitter terminal. It could be a resistor or a transistor with some dynamic resistance. We'll see that. But somebody should be there. Directly emitter terminal, you cannot connect it to ground, right? So there should be somebody at the emitter terminal, right? It gives stability of IC/DC independent of beta. It gives thermal stability to the circuit. RE increases your RN and R0, but it decreases what gain? Voltage gain, right? Now, what is this thermal stability? The thermal stability to the circuit. What do you mean by thermal stability? Thermal stability. So we'll have a simple circuit with RE. I think we will take the basic one, right? 4 volt, 3.3 K. Do you remember? Suppose I give 4 volt here, VBB. This is 3.3 K RE. This is RC. You have VCC here, and there is IC. All right. Here there is VB. Now this is IE. Okay. So what happens if temperature increases, right? If temperature increases, then the leakage currents in a transistor will increase IC. So if suddenly temperature, so you can take a hair dryer, you can just take a hair dryer and just blow hot air onto the BJT. So if you put a milliammeter in series with RC, you'll realize that when the temperature is increased, the milliammeter will show a reading that's not stable. Your IC is also going to increase. If IC increases, your IE will also increase, or IERE will increase. Your IERE will also increase. So what happens when your IERE increases? Your VB equal to VB minus V. Am I right? VB minus V. Who's there at the base terminal? VBB. Here IERE. Now what happens if IERE increases? If IERE increases, your VB will decrease. Your VB is going to decrease. So we know IC and VB, they are non-linearly related, right? What is IC? IC equal to IS into E power VB by VT. So if VB decreases, then naturally your IC will decrease. Now, did an op-amp give you the same scenario? Do you remember op-amp? I told you, for an op-amp, your V0 was a concern. If V0 increases, then your V1 will increase. If V1 increases, there a VD is going to decrease. That VD is nothing but your VB here, your VB. So if VB decreases, your IC will decrease. Have you seen the same scenario in a negative feedback of an op-amp, right? So, and what is the other name we have given for negative feedback? What is the other name we have given for negative feedback? Is it regenerative or degenerative? What is the other name we have given for negative feedback? Regenerative or degenerative? Degenerative, right? So that is why this is called a degenerative resistor. Because this resistor is going to give you negative feedback, right? How? If IC decreases, then your IERE will also decrease. If IERE decreases, your VB will increase. If VB increases, your IC will increase. So what does this scenario tell you? What does this scenario tell you? Suppose if this VBB is 4 volt, this is 3.3K. What happens? Now, somebody takes a hair dryer and just blow hot air onto the BJT. Now, you cannot claim that your IC is exactly 1 milli, right? This should be 1 milli, of course, but it won't be 1 milli. So what happens is, the moment the temperature in a transistor increase, this current might increase, right? Might increase, right? It was 1 milli and it increases. Once it increases, the next iteration, it has to decrease. If it decreases, the next iteration, it has to increase and decrease and increase, and it will come back to the point where it has started. So we've seen this scenario even with an op amp in negative feedback. So we've clearly explained there. See, that's the reason op amp was a first topic, right? So because op amp is like a universal block diagram. So when you understand negative feedback, you can understand the benefit of an emitter resistor. So when IC increases, the increase of IC has decreased IC, and the decrease will further increase. So finally, it will come back to the point of 1 milliampere, which is 4 volt, 3.3K. Within no time, he has to come back to 1 milliampere. So that is why the emitter resistor gives what feedback? So what we have to write here, note emitter resistor gives negative feedback. Emitter resistor gives negative feedback, and negative feedback gives stability to the circuit. Stability to the circuit. So your IC/DC is going to be constant. Is going to be constant. And I tell you, when I remember when we were using the power transistors, right? So the power transistors, I still remember because of the cumulative effect. If temperature increase, IC will increase. Then IC increases, temperature increase. Temperature increase. There's something called the runaway problem. There's something called what problem? Runaway problem. So to stop the runaway problem, what we used to do is, if you have a power transistor, we used to put small 1 ohm resistors. For example, we had transistors like this, the power transistors like this, say the class B complementary symmetry, and the size of heat sinks used to be very big for such circuits, right? I mean, what is a heat sink? It's something like an aluminum. Have you seen a heat sink? Heat fins, right? There's so many types. So with the aluminum sheets that we use over this to dissipate the heat used to be very big. Instead, what we felt was you can cut down the size of an aluminum sheet that you're putting over this transistor by just connecting a small 1 ohm resistors here, 1 ohm like that. So you can use a wire wound resistor, right? A big size one. So if you put 1 ohm resistor, then the size of heat sinks will come down. So emitter resistor should be there. Without an emitter resistor, you cannot expect to design any circuit. Every circuit should have an emitter resistor, because it's not just the stability of RE, even the size of heat sinks will come down, because the emitter resistor is going to give you thermal stability to the circuit. And of course, in AC analysis, I will prove the Rn, R0 voltage gain later, right? So don't forget that emitter resistors will bring stability, thermal stability to the circuit. So you can combat with temperature now. Even if temperature suddenly rises, the current will increase and then finally decrease, and it will come back to the point where it has started. Okay, so far so good. Finally, we came to this equation. Just observe this equation here. IC is still dependent on VB, IC is still dependent on VCC, right? Now the second problem, problem 2. The first problem is beta. Beta dependency we have eliminated. The second problem is temperature. Temperature or drift, thermal drift. Drift problem. So what is this temperature or drift problem? If temperature increases, if temperature changes, VB will change. If VB changes, your IC will change. So we know that VB is going to decrease by 2.5 millivolt for every 1 degree rise in temperature. So if temperature changes, your VB will change. If VB changes, your IC will change. So this is called drift. So every analog circuit is subjected to some sort of a drift there. The currents and voltages are going to shift from their values because of the temperature variation. Okay. So fine. If temperature changes, VB is going to change. If VB changes, your IC will also change, right? Now, how are we going to eliminate this VB dependency? So let us go back to the what you call the so finally here your IC was approximately VCC R2 by R1 plus R2 minus VB by R. Right? Now to eliminate this VB, what can I do? To eliminate this VB, can I add one more VB here? Can I do this? Do this. I mean, it looks a little childish, right? So you have a minus VB equation. What happens if I put a plus VB here? If I connect plus VB here, then the minus VB is going to cancel plus VB, right? And then your current is now going to be free from VB. If the current is going to be free from VB, indirectly it's going to be free from temperature or drift, right? So that's the question. Now, how are we going to do this? Right? There's R1 and R2. Now, I have to add VB now. I have to add. What if I connect a PNP here? I connect a PNP, and then this output, I'll give it to an NPN. Right? Okay, so what happens if you connect a PNP? There's a diode here, and there's a diode. We have even seen this kind of a construction in a sampling gate, right? Suppose there's some node voltage Vx here. If I go up, I have to add. If I come down, I can subtract. So I'll just go up here. This is going to be Vx plus 0.7. Am I right? 0.7 or VB. And if I come down, this is going to be Vx plus 0.7 minus 0.7. It is going to be Vx, right? Now, what happens if temperature change by 4 degree. For 1 degree, there's 2.5 millivolt. For 4 degrees, there's going to be a 10 millivolt change, 10 millivolt change. So I have two transistors, QN and QP here. Sorry, QP is the PNP here, QN is the NPN. So if I connect them in this fashion, if you add 0.7 here, you're going to subtract 0.7. So if you add 0.71 because of the temperature, you're going to subtract 0.71. So the net effect is always going to get cancelled. The net effect is always going to get cancelled. So if there's a 10 millivolt rise in QP, there's going to be a 10 millivolt fall here. Or if this falls, this rises, right? And what is the net effect? The net effect is your IE. Your IE is going to be Vx by Re. So if your beta is large, what is Vx by voltage division? It is VCC R2 by R1 plus R2 by Re. By Re. This is approximately your ICDC. So unlike the previous equation here, you had this VB. So we try to cancel that VB by using some sort of a diode compensation, right? So it's like a VB compensation. This is called the VB compensation, right? But please remember, note, if you want to eliminate, this eliminates the drift problem or temperature problem. If you want to eliminate the drift problem or the temperature problem, what is more important is you have to buy two transistors with the same temperature coefficient. You have to buy, that means don't say temperature coefficient with the shopkeeper, right? You have to say the language they use is called TEMCO. It's called TEMCO. Both transistors should have the same TEMCO, right? Temperature coefficient, these names are, the only electronic guys know it, but the colloquial way of saying is TEMCO. TEMCO stands for temperature coefficient. So note, right? Both transistors, right? Both the transistors should have the same temperature coefficient. Both the transistors should have the same temperature coefficient. If they have the same temperature coefficient, then the net effect is going to get cancelled, right? So then IC is independent of PB. It's independent of what? PB, right? Is independent of VB. So what is this technique called? This technique is some sort of a VB compensation, right? IC is independent of VB with the VB compensation, with the VB compensation. The diode drop compensation, right? So both the transistors should have the same temperature coefficient. Then your IC is independent of VB, right? And that's the reason you are able to bring back the same voltage. Can you see here? Can you see this point here? This voltage comes here, jumps. Previously, what happened was, this is the dot here and this is the dot. Can you see? And here you have a VB drop. VB drop. So now, if temperature changes, your VB will change, your IC is a function of VB. But what did we do here? This is Vx, we bought back the same Vx here. We bought back the same Vx there, right? Now the same question, if you have values here, 1K, 2K, right, 5K like that, then it becomes a problem. Are you getting the same theory? It can become a problem. The examiner might ask, what is the emitter current IE if beta is large? The emitter current IE if beta is large is VCC R2 by R1 plus R2 by R. Are you getting VCC R2 by R1 plus R2 by R? So both transistors should have the same temperature coefficient. Then IC is independent of VB, right? Now tell me, how can I bring back the same voltage here? Is there any means that I can bring back the same voltage here? Because two transistors with the same temperature coefficient is costly actually, right? They are called batch transistors. So you have to buy two transistors, the batched one, exactly the same characteristics. So that's a costly affair. But we can even solve this problem just with 2 rupees, right? So what happens if I give this node to a non-inverting terminal of an op-amp and this node, so what happens if I connect it in this fashion? So with very less money, we can bias the BJT independent of RE, independent of temperature, right? So if somebody says, sir, that's costly to buy two transistors with the same Tempco, no problem. So what we are going to do is, this node is here. I want this node to be equal to this node, right? So I just bring back here like this. Connect it like this. Now what happens if this is Vx? It's very simple. When a positive voltage is given to positive terminal, the output is positive. The output VOP is positive. When VOP is positive, the diode is forward bias. There is negative feedback. So what happens in negative feedback? Op-amp tries to keep both the potentials same, right? Op-amp will bring back the same voltage Vx at this point here, This is exactly what we got with two transistors with the same temperature coefficient. So this was Vx, and the same Vx from the voltage divider appeared at the emitter terminal, And we solved that problem just with 2 rupees here, just buy one op-amp and connect it here, right? Now what happens to RE? IE. IE is going to be, of course, this is a gate problem, right? I'm not giving you values, R1, R2. So what is IE? IE is going to be Vx by RE, right? And what is Vx by voltage division? It is VCC R2 by R1 plus R2 by RE. And what happened to your, this is approximately, ICDC. Now what happened to your VB, right? That VB is blanketed with the 0.7, like how we have stuffed that 0.7 in a precision rectifier, and the output was never a function of that 0.7. It was only a function of VOP, right? So similarly, here there is 0.7 here. If you go up, you have to add. You have to go up if you add, right? So what is VOP? It's going to be Vx plus 0.7. So your transistor current is independent of 0.7. Only your VOP is a function of 0.7. So it is going to be VCC R2 by R1 plus R2 plus 0.7. So it is the op-amp who's going to drive the transistor now. And please look at the divider. Look at how beautiful this divider is. It's so stiff. Because the base current here, the current here is going to be 0. Op-amp draws no current, right? But look at these useless voltage dividers here. So any voltage divider, there's always a problem of base current coming, right? So there's always, the divider is not that stiff. I was just claiming, right, beta large. But just with 2 rupees, you have 2 advantages here. One, you can blanket that 0.7, and the 0.7 is stuck there. If temperature changes, this 0.7 become 0.71, 0.72, 0.69, 0.695, but your Vx is always the same Vx here, right? As long as the transistor is on, the Vx and the Vx is same. Your operating current is independent of temperature, right? Or drift problem. So let me make a note here. Op-amp with negative feedback, will totally eliminate the problem of drift or temperature. Op-amp negative feedback will totally eliminate the problem of drift or temperature. So now we understand that the 0.7 is only an assumption, right? It's only an assumption the examiner will give you, but that 0.7 is going to change by temperature. Now you might think that what is there in that change in 0.7? It's hardly a millivolt, yes or no? It's hardly a millivolt here, but no, you cannot neglect that, for 2.5 millivolt or whatever. The reason is, suppose, just imagine you're using your cell phone. You're using a cell phone in a place like Russia, where there is minus 30 degrees, and then you came directly to Delhi, where there is 45 degrees in summer. So the same cell phone which you're using should work in the same fashion at a temperature of minus 20 and a temperature of plus 50 degrees also. Are you getting? So if there is a 70-degree variation there, so definitely even that 2.5 millivolt multiplied by 70, that's a big number. Are you getting? So don't think that VB equal to 0.7 is only our assumption, but there will be a slight change in VB. And that change, when the temperature variation is huge, that change cannot be neglected, right? Definitely the performance of the amplifier will not be same, right? Then you cannot say that if you carry this to Russia, it will not work. If you come to Delhi, it will work. But Hyderabad is a better place. No, that's not how an analog engineer should design, right? Irrespective of variation of temperature, your current should always be constant, right? So op-amp with negative feedback will totally eliminate the problem of drift, right? This is a load. Now suppose if you don't want a floating load, this is a floating load, and if you want the load to be connected to ground, how can I make this transistor ulta-pulta like this? So that my upper load will come down and the floating load is going to become a grounded load. We have done that in the 2 transistor problem, right? So the upper transistor down. How can I do that? Huh? How can I do that? How can I flip the transistor? Huh? Very good. PNP, is it not? Very good. So I'll make a note here. Current sources biased with NPN transistors. NPN transistors have floating load. Whereas using PNP transistors, we can have grounded load. So the same circuit, if you want to flip it, you can do it like this. Here you can connect your load RC. This is your R. And just see where is the feedback. The feedback, the inverting terminal has to go to the emitter node. The inverting terminal has to go to the emitter node, right? So be careful while drawing. The inverting terminal has to go to the emitter node, right? So just analyze this circuit. We'll solve problems on this, right? We will solve a problem on this. But before that, what is Vx quickly? It is VCC R2 by R1 plus R2. Am I right? Then I told you, whenever you solve negative feedback problems with diodes and transistors, you have to first treat a transistor as a comparator. You have to first treat a transistor as what? A comparator. And when you remove the transistor from here, you can check here, the anode is directly at VCC. The anode is directly connected to VCC here. Are you getting right? So there's just remove the transistor. Okay, let me, I don't know. Yeah, just take your hand and put on the BJT, right? Just close the transistor. When you close the transistor, you have VCC directly at the anode. So there's a possibility that the diode is on. So once the diode is on, the same Vx is going to appear here. This is Vx. Am I right? This is VOP. Then what is your IE? What is your IE? IE is going to be VCC minus Vx by R. What is Vx? It is VCC R2 by R1 plus R2. So this is going to be VCC R1 by R1 plus R2 into R. This is your IE. This is your IE, and IE is approximately ICDC. So it's very simple. In the previous example, the voltage was this drop. The voltage was this resistor drop, VCC R2 by R1 plus R2 by RE. In this problem, it is VCC R1 by R1 plus R2 by RE. Because the whole voltage RE is here, this node and this node are same. Am I right? This node and this node are same. This node and this node are same. Am I right? So the R1 is going to appear, the drop across R1 is going to appear across RE. Drop across R1 is going to appear across RE. So directly you can do IE equal to VCC minus Vx by RE. Substitute Vx there. You're going to get VCC R1 by R1 plus R2 by RE. So let us solve one or two problems on this, then you will know the exact voltages and currents in the circuit. So a load that is not connected to ground is called what load? Floating. A load that is connected to ground is called a grounded load. This is a grounded load. And if a load is connected elsewhere, it is called what load? Floating load, right? Anywhere else, it's called floating. But if it's connected to ground, it's called a grounded load. So let's take a simple problem. find VE, IE, IC. Beta is large. V beyond 0.7. Find VE, IE, and IC. Very, very simple problem, right? Okay, so let's solve. So I told you, whenever you're solving op-amp with diode problems, you should first treat op-amp as a comparator. Treat op-amp as a comparator. As a comparator, right? So what is this comparator here? The non-inverting is at 4 volt. Am I right? Now just remove the transistor there. The inverting terminal is, this is VOP. The inverting terminal is connected to ground. Is connected to ground. So you have 0 volts here, right? So this is VOP. Now you tell me, when the non-inverting is at 4 and the inverting is at ground, your VOP is positive. If your VOP is positive, what will happen to the diode? The diode is going to get on. The diode is going to get on, right? So that diode is the base to emitter junction. So when you don't connect a transistor, this end is at ground. So you have 4 volt here. So definitely the moment you switch on, your VOP is going to get positive and the diode is on. But once the diode is on, this is what feedback? Negative feedback. So you can apply virtual short now. You can apply virtual short. Please don't apply virtual short when there is no negative feedback. When there is no negative feedback, please don't apply virtual short, right? So let me have here, this is a 4 volt minus, yeah. Resistor same, yeah, oh, 12 volt. Okay, so whatever it is, now tell me if this is 4 and VOP is positive, the diode is on. Once the diode is on, there is negative feedback. So your V1 is equal to V2. So this node is also at 4. Then what is IE? What is IE? Your VE is equal to 4 volt. And what is your IE? IE equal to 4 by 2K is going to be 2 milli. All right. Now what is VOP? VOP. IE is same as IC. IE is same as IC. What is VOP? It is 4 plus 0.7. It is going to be 4.7. So if temperature changes, this 4.7 will become 4.71, 4.72, 4.73. But here you will always have 4. So your IE is equal to IC. IC is approximately IE if beta is large. If beta is large, okay? And once you find IC, what is your VC? what is your VC? If you want VC, right? Your VC is going to be VC minus V. VC minus V. What is VC here? If this current is 2 milliampere, your VC is going to be 12 minus 2 milliampere into 1K. This is VC minus V is 4. So VC, this is the VC voltage and this is V. All right. So 12 minus 2, that is 10. 10 minus 6 volt. So VC is positive. So is VC greater than VE? True. That means BJT is in what region? Active. BJT is in active region. When a positive voltage is given to positive terminal, the output is positive. There's negative. Orally, you can do it, right? No need of all steps. Directly, this is negative feedback. So this node is going to be 4. The current is going to be 4 by 2K, 2 milli. So this is 2 milli. 12 minus 2 is 10. So 4 here and 10 there. So naturally, BJT is in what region? Active region, right? Okay. Now, the same problem, let's do with the PNP now. So let me give the same 4 volt here, right? So I've given some resistor values here. Okay. Yeah. So the question is find V, IE, and IL if beta is large. If beta is large. The B bit is find the value of load RC such that the BJT is in EOS condition. EOS. What is EOS? It is the edge of saturation, right? You have to find the value of load RC such that the BJT is in EOS. And we know what is VCE or VEC, right? VCE mod you can take. VEC is nothing but 0.2 volts, right? For saturation. So your VCE or VEC is going to be 0.2 for saturation. So let's see how the PNP diode is going to get on now, right? So all these problems where the op-amp with transistors are at negative feedback, the op-amp is in negative feedback, it is definitely going to eliminate the problem of VB or temperature. Okay, so let us solve. Treat op-amp as a comparator. Treat op-amp as a comparator. The non-inverting is at 4, but just remove the op-amp. Here you have a 12 volt here, right? 12 volt. So the 12 volt is connected to inverting and the non-inverting is 4. The same thing here in the previous example, we had the voltage divider here, if you remember, right? Yeah, the voltage divider. So even in this case, the Vx is much larger than, smaller than VCC. So if you open circuit the op-amp, you know that the inverting voltage, where is it? Oh. Yeah, the inverting voltage is at 12, the non-inverting is at 4. So your VOP is negative. Your VOP is negative when you switch on. And after that, what is the difference between a comparator and a continuous comparator? What is the difference between a comparator and a continuous comparator? If you just compare non-inverting with inverting and your VOP is positive or negative, it's a comparator. But if there is a negative feedback and you take that voltage and backtrack, compare, and then take it and compare and compare and compare and compare, a continuous comparator is an amplifier. So what is the difference between a comparator and an amplifier? If somebody asks you, what will you say? If you compare only once in open loop, it is a comparator. If you give negative feedback and continuously compare the values, then it's a continuous comparator. That means it's an amplifier. It is going to set up virtual ground. For virtual ground to set up the negative feedback, there has to be a diode in this fashion. Because your VOP is negative. Once the diode gets a bang, then it becomes a continuous comparator. Compare and compare and compare and compare. It keeps comparing such that the voltage at non-inverting is going to appear as voltage at inverting. So this node is going to be the same value. So your VE, so there is, the diode is on, right? The diode is on, the transistor is on. So once it is on, there is what feedback? Negative feedback. So if transistor is on, we can apply virtual ground. We can apply virtual ground. So let's apply virtual ground here. What is VE? VE is going to be 4 volt. VE is going to be 4 volt. So if VE is going to be 4 volt, so it's 4. Here you have given how much? 12 and 4K. This is 12 volt. It is 4K. So what is your IE? If V is 4 volt, your IE is 12 minus 4 by 4K. 8 by 4, 2 milliampere. And your IE is approximately IL. Your IE is approximately IL or IC. IL or IC, right? So this is A bit. This is A bit. So simple bit. Once you know that there is negative feedback, your voltage at non-inverting is voltage at inverting. And then this is 4. This is orally you can do it, right? This is 4. This is 4. Your current is 12 minus 4 by 4K, 8 milli. So that's the answer. Now, what does B bit say? The B bit says that what is the condition for EOS? In EOS, we have to respect the IC equal to beta IB, and IC by IE is beta by beta plus 1 condition, which is the active region condition, as well as the saturation. In saturation, your VCE or VEC is going to be 0.2. It's going to be 0.2. Here there is a current of 2 milliampere. So this current should also be 2, right? And here there's 4K, 12 volt. So this is 4 volt, right? Now you tell me, what is 4 volt, the voltage from here to ground? 4 volt equal to 0.2 plus 2 milli into RC. 4 volt equal to 0.2 plus 2 milli into RC. From here, RC is 3.8 by 2 milli. It is going to be 1.9K. It is going to be how much? 1.9K is your RC. So if RC is greater than 1.9K, the BJT is in saturation. If RC is less than 1.9K, it is inactive. If RC is equal to 1.9K, it is in EOS. It is at the edge of saturation. It is at the edge of saturation. Okay, now all of you, I want you to solve this problem orally, right? Don't touch the pen, keep your pen aside, just look at the circuit and just tell the answer, right? Just don't do anything. Please don't forget what is the procedure. VE, IE, IC, VC. VE, IE, IC, VC. Never forget that. VE, IE, IC, VC. Just look at the circuit and tell me the answer. Find IL. Beta large. Right? Consider BJT in active. Just tell me orally, what is the answer? Orally, don't do anything. VE, IE, IC, VC. VE, IE, IC, VC. How will you solve? What is VE? Or what is VE1 here? When a positive voltage is given to positive, the output is on, the diode is on, so you're going to have how much here? Because of negative feedback, 2. If this is 2, then what is the current I? If you know VE, then what is IE? IE is going to be 2 minus of minus 3 by 2.5. Then it is how much? How much is that? 2 milli, right? If this is 2 milli, this is also 2 milli. Then what is VC1? What is your VC1 then? 12 minus IC1 into 4K. If IC1 is 2 milli, 2 into 4, 8. 12 minus 8 is going to be 4, right? 12 minus 8 is going to be 4. So this is at 2, this is at 4, BJT is an active region, right? So this is VC1. So this node is also VC1. So tell me, this is 2, this is 2, so this is 2, this is 2 milli, this is 2 milli, 12 minus 8 is 4. If this is 4, this is 4. If this is 4, when this is 4 here, this is 4, this is also 4, then what is the current here? IE2. IE2 is same as IL. 12 minus 4, 8, 8 by 100. So that's the answer, right? So this is given for 10 marks in IES exam, right? So you can do it orally now, right? So VE, IE, IC, VC, 10 marks problem. It hardly takes 10 seconds for you to do it, right? So it's much quicker, provided you know virtual ground and you should know the procedure, VE, IE, IC, VC. So once again, tell me orally, if this is 2, what is this? 2. Then what is the current here? 2 minus of minus 3 by 2.5, it's 2 milli. Then this current is also 2 milli. 4 2s are 8. 12 minus 8 is going to be 4. This is 4. This is 4. This is 4. 12 minus 4 by 100. So that's the answer, right? So this is going to be how much is the answer, right? So let's do the solution. Oh, we are done doing orally, but what's the solution? You tell me. First step, VE1. VE1 is how much is VE1? 2 volt. What is IE1? 2 minus of minus 3 by 2.5. It is 2 milliampere. This is same as IC1. The same as IC1. IC1 is approximately IE1, just 2 milliampere. Then what is VC1? What is VC1? It is 12 minus drop. 12 minus IC1 into 4K. 12 minus 8, which is 4 volt. So this ends Q1. So the first transistor is done, right? Now we'll have to go for Q2. In Q2, what is VE2? VE2 equal to VC1, right? And please, once again, the PNP transistor, how is it getting on? How is the PNP transistor getting on? Just take your hand like this and close the PNP. Just don't see the PNP. Now, inverting terminal voltage is directly 12 and non-inverting is at 4. Inverting is given to 12, non-inverting is at 4. So the output is negative. So when you have a diode like this and your VOP shoots up to negative, definitely the diode is on. Once the diode is on, finish, the story changes. Op-amp is no longer a comparator, it's a continuous comparator. Take the voltage, backtrack. We have seen how the voltages will keep changing. Backtrack, 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 backtrack. And finally, it will sleep only when the voltage at non-inverting comes to voltage at inverting. So what's a stable point for an op-amp is virtual short. The voltage at non-inverting should be equal to voltage at inverting. VE2 is VC1. VC1 is going to be, how much is VC1? 4 volt. And what is IE2? IE2 is nothing but 12 minus 4. 12 minus 4 by 100. It is 8 by 100. It is going to be 80 milliampere. And your IL is nothing approximately IE2, which is 80 milliamp. Right? So this is a 10 marks problem in IES exam. And the worst part is the same problem is again repeated in IES, next time for 12 marks. And that too, the examiner he didn't even change the values. So he's so lazy, right? He didn't even change the value. Same problem is again given for 12 marks. Once he gave for 10 marks. Some questions in IES exam, they do repeat, right? So that's how it is. So VE, IE, IC, VC. VE, IE, IC, VC. Okay, so what is the EOS condition we've been mentioning? In EOS, nothing is there. But the currents here are the active region currents. Extra thing what you have to do in EOS is the transistor VC you have to take 0.2. You have to take VC as what? 0.2. So once you take 0.2, what will happen if you take 0.2 here? If you take 0.2 volts here, then it puts a limit on your RC, right? It says that if RC is 1.9K, if RC is 1.9K, that is when the transistor will slightly enter into what region? Saturation. Just imagine, give me some simple value. What is 4 minus 0.2? What is 4 minus 0.2? 3.8, yeah. If my RC is 3.8K, what will happen? If my RC is 3.8K, what will happen? Right? 4 minus 0.2 is 3.8. 3.8 by 3.8K, the current is going to be only 1 milliampere. Is going to be 1 milliampere. Now, but the entering current here is 2 milliampere and only 1 milliampere is coming for 3.8. Now, what happened to the extra 1 milliampere? That 1 milliampere is sinking through the base region here. It is sinking through what region? Base region. What if this is RC is 1 mega ohm? What is RC is 1 mega ohm? 3.8 mega ohm. If your RC is 3.8 mega ohm, 4 minus 0.2 is 3.8. 3.8 by 3.8 mega ohm. 1 microampere of current will flow. But 2 milliampere of current here, right? 2 milliampere and only 1 microampere. What happened now? Complete 2 milli, almost 2 milli, will nicely sink through the base region. So nicely the base region, that fellow will put one straw and he'll suck all that complete signal. See, IB is greater than IC by beta. The transistor will enter into what region? Saturation. In saturation, your IB is almost equal to IE here if your RC is 1 mega ohm. So it's a very dangerous resistor, RC. If you keep increasing that resistor, the BJT will go to what region? Saturation, right? What if your RC is only 100 ohms? If your RC is 100 ohms, then 2 milliampere into 100, that is going to be 2 milliampere into 100, 200 millivolt here, right? So it's 200 millivolts. So that means there's a wide gap between emitter and collector. It will not be 0.2, right? It will be a large value here. Collector current and emitter current both are same only when your VC is positive, right? So if you put low value of RC, then your VC is positive. If you put high value of RC, what will happen if you put high value of RC? All that emitter current is now going into what current? It is going into base, right? The transistor is going to sink through the base. So that's dangerous, right? It's dangerous. But the examiner mentioned consider BJT inactive, so fine, right? VE, IE, IC, VC. VE, IE, IC, VC. check the region of operation. Yeah, I think this might be the last problem. It's 8:50, right? So, okay, check the region of operation of BJT. Right? Check the region of operation of BJT. You can take beta 100 or beta 99 just for a change, right? Beta 99 and VB on equal to 0.7. This is A bit. B bit is find IE, find IE and VOP if Vn equals 2 volts. Find IE and VOP if Vn equal to 2 volts, right? This is a gate problem given by ISC Bangalore, gate 2002 for 5 marks. So till 2002, we had good 5 marks questions, right? And from 2003, pattern got changed. There were no 5 marks, only 1 mark and 2 marks. So this is given by ISC Bangalore, gate 2002 for 5 marks, right? So how old were you at 2002? 2002, right? So you might be very young at 2002. Young or I think you're kids, right? 2002 is. Hmm? 1 year old, 4 year old, 3 year old. Okay. Okay. So how do we solve this? You have to treat op amp as a comparator. Treat op amp as a comparator. The non-inverting is given to Vin, all right, Vin. So what is Vin range? It is 0 to 5 volt. Can you see here the lever here? Can you see the lever here? It moves from 0 to 5. Moves from 0 to 5, 0 to 5 like that, right? So it's like a potentiometer, right? So it is varying from 0 to 5. So your Vn is 0 to 5. But if you just close the transistor, if you just remove the transistor, the inverting terminal is given to minus 15 volt. So what should be my VOP? Vin is positive, inverting is at negative voltage, so your VOP is definitely positive. If your VOP is positive, what will happen to the base to emitter junction, right? The base to emitter junction is forward bias. The base to emitter junction is forward bias. So let me make a note of that, right? For all voltages Vin, the VOP is positive. VOP is positive. The base to emitter junction is forward bias. The base to emitter junction is forward bias. When it is forward bias, you can apply virtual ground, right? You can apply virtual ground now, right? you can apply virtual ground. This is 10 ohms. So what is your V? Your V is going to be Vn. The V is going to be Vn, right? And what is the range of Vn? What is the range of Vn? Oh, this is short, plus 50. V is Vn, and Vn is from 0 to 5 volts. 0 to 5 volts, right? What is your VC? VC is going to be 15 volt. So what is your VCE? VC equal to VC minus V. It is 15 minus V is your Vn. V is your Vn. So VC, Vn range. What is Vn range? Vn range is 0 to 5. Your VC range is, if you substitute 0, 15, and 5, so it's 10 volt to 15 volt. Because VC is positive, is VC greater than V? True. That means BJT is in what region? Active. BJT is definitely in what region? Active. Because if this is Vn, this node is Vn. Vn is from 0 to 5. Here you have 15, so definitely it is an active. But orally you can tell, is it not? This is 0 to 5. Collector is at 15, so BJT is in active region. Now what is B bit? B bit says that if your Vn is how many volt? 2 volt. If your Vn is 2 volt, then what is IE? If your Vn is 2 volt, what is IE? So this is 2 volt. Now tell me, what is IE? Your V is also 2 volt. 2 volt. This is B bit. And what is IE? IE is 2 minus of minus 15 by 10. That is going to be 1.7 ampere, right? It could be a power transistor. The gate examiner would have put a power transistor there, right? So it doesn't matter, 1.7 ampere, that's a big number. Now, what is VOP? What is VOP here? Oh, this is VOP. This is going to be VB. What is VB? What is VB? VB is going to be 2 plus 0.7. It is 2.7. VB is going to be 2 plus 0.7. It is 2.7. If IE is given, what is IB? IB is IE by beta plus 1. It is 1.7 by beta is 99 plus 1, 100. So it is 1.7 by 100. This is IB. See, what am I doing? I'm calculating everything. So this is the last problem, and I don't know what to calculate. I'm just calculating what is the question that I've given. Find IE and VOP. Okay, IE we have already calculated. What is VOP? Tell me VOP. This is VB, we already know. IB, we already know. 150 ohms. VOP, we don't know. Yeah, tell me. IB equal to VOP minus VB by 150. So 1.7 by 100 equal to VOP minus VB is 2.7 by 150. So that's it, you get VOP. So some calculator, tell me in this, what is VOP? 1.7 by 100 into 150 plus 2.7. What is VOP? What is VOP? What is VOP? 5.25. Somebody is telling me 5.25. Right? So 2.7. So yeah, it's close to 5.5. Good. So let me do this orally. If this is 2, this is 2. 2 minus of minus 15 by 10, 1.7, right? That is IE. What is IB? 1.7 here by 100. And this node is 2 plus 0.7, 2.7. So now IB is VOP minus VB by 150. So you can substitute, right? So this is a 5 marks problem given by ISC Bangalore. So BJT is in active region, that is A bit. The B bit says this. Okay, so with this, we come to an end for today. You can ask the questions if you have.
Hello, sir.
Hello.
Yeah, tell me.
Sir. Good evening, sir.
Yeah, good evening.
Sir, in emitter bias biasing, you said that if R is greater than RB by 1 plus beta, then
Yeah.
base potential increases, no, sir?
Yes, yes.
Then how it is, how that condition is possible? I mean, I did not understand that condition, sir.
What is the condition? BJT will go to saturation, I'm saying.
Yes, sir.
That circuit will not work, I'm saying.
Base potential increases.
Yeah, see, that's what, no. If RB drop you are neglecting, that means complete VCC is there at the base terminal. No?
Yes, sir. Yes, sir. Got it, sir.
Okay, good, good.
Sir, and again, in 6F, sir. 8F, sorry, sir.
Yeah.
Sir, in this B bit, you are asking to find the time, no, sir, for saturation condition.
Yes.
Can we take directly VC equal to VE and then do it, sir?
VC equal to?
VE.
VC. VC is collector voltage. How collector and emitter are same? With
No,
0.2
sir.
I've given, no?
If it is 0, sir, then we can.
If it is 0, yes. VC and VE are same. In gate problem, V is given 0.
Then directly we can get
Yeah, emitter voltage. What is there? In my case, 0.2 you will add. That's all, no?
Yes, sir. And again, sir, you said continuous comparator, no, sir?
Yeah, that's what the op-amp was doing in when I started op-amp negative feedback. We have written on table, no?
Yes, sir.
One big table. That is what is called continuous comparison. Keep on changing the values until the voltage at non-inverting becomes equal to voltage at inverting.
Okay, sir. Okay.
That is called virtual ground.
Yes, sir.
Yeah.
Sir, and then for diodes problem, you said, no, sir, something like maximum potential difference should be there so that it will be on.
Yeah, anode should be greater than cathode. That's all.
Not that, sir. At the same point, triggering point, if it should be maximum potential, then only the diode will be on.
No, if 2-3 diodes are tied at a common point.
Yes, sir. I remember that, but I did not. I mean, I don't know how it is possible. I mean, I did not. I forgot. Sir.
See, if you think 2 diodes are on, then you are violating Kirchhoff's law. I'm saying it's not possible. Suppose 3 diodes are there. 3 are on means you don't know. See, can you tell in your house there is 230 volts or 110 volts or 115 volt? You
No,
cannot
sir.
say.
No.
At any point there can be only one voltage, no?
Yes, sir. Yes.
So if 3 diodes are on, can you say the voltage can be 1 or 2 or 3? That is wrong.
Yes.
Voltage means potential. It's height. What is the height of the tank? It is 1 meter, 2 meters, some fixed value. It can be 1 meter or 2 meters or 3 meters. It's not possible. No? You are violating one. The height should always be same. Yes or no?
Yes,
Should
sir.
always be 1. You cannot have 2, 3 values.
Yes, sir.
Yeah.
Sir, and again 4F, sir.
Huh?
4F, sir.
Yeah.
Sir, for no value of V in both transistors can be inactive, no, sir?
No. It is emitter is then ground, no?
That's what, sir.
If base is also ground, both are off.
Oh.
That is why, what is the transfer characteristics for this? We have already drawn. If you take Vin on x-axis, V0 on y-axis, the transfer characteristics is till 0.7 volts, it is not on. Till minus 0.7, it is not on. After that, you will get this. See the diode circuits problem. You will know.
Yes, yes.
Yeah, this we have drawn, no? Same thing for BJT also.
Okay, sir.
This is a dead zone between plus 0.7 and minus 0.7. No output will come if you give V in anywhere between plus 0.7 and minus 0.7, because both these diodes, can you see these diodes here?
Yes, yes.
None of the diodes will be on, no?
Yes, sir. Yes, sir. I remember.
Okay then.
Sir, thank you, sir.
Yeah.
And your
Next.
teaching is very nice, sir.
Thank you. Thank you.
Hello, sir.
Yes.
Sir, yesterday you said something RL is changes, VC is changes, and then VB is changes and base with modulation in base.
That we will see next class when I take up a cascode amplifier again. Okay.
Okay,
Base
sir.
with modulation, no?
Okay, sir.
Yeah.
Yesterday I asked the doubt regarding op-amp draws current, no, sir. Yesterday,
Op-amp draws?
no current. Yesterday I asked, no, sir.
Yes, yes.
Sir, if in the initial days our classes we did some problems regarding negative feedback and positive feedback. In that also it doesn't draw any current, sir.
Yes. In any problem, op-amp will not draw current because its input resistance is very high.
Very high. But when it is connected to series shunt feedback, then it draws current, right, sir?
No, but the device will not draw. Feedback resistors will draw and you will get an output.
Okay, okay, sir.
RF resistor, R1 resistor, R2 resistor, they will draw current.
Okay, sir.
But device will never draw.
Never draw. Okay, sir. Sir, in page number 6F. Sir, here T equal to 0 plus, na, sir. That means the switch is closed, right, sir?
Yeah.
So why didn't you consider the closed switch, sir? You are choosing the capacitor path.
Because the arrow, can you see this arrow here?
Yes, sir.
It tells that you have to open that switch for 0 plus.
Okay.
The arrow indicates that the switch which was closed, you have to pull it and open it.
Open it. If they didn't mention about arrow, we need to close it, right, sir?
No. So when a switch is there, an arrow will be there. Suppose I'm having a switch here like this.
Yes, sir.
And if he puts an arrow like this,
we need to close it.
It means at T equal to 0 plus, it was closed.
Okay.
And it is open for a very long time.
Okay, sir.
Here we are opening it. That means it is closed for a very long. Simple. Suppose if there is a switch in your room,
yes, sir.
and in the room fan is already there. Fan
yes,
is rotating. It means what? The switch is on.
On.
Now when you go to that switch, what you will do? Will you again switch it on? No,
sir.
you will switch it off. Suppose if the fan is not there, I mean there is no power to the fan. That means it is off. Now you are operating on that switch. That means you will switch on. Are you getting?
Yes, sir.
So the arrow will tell that what is the previous state of the capacitor. Now this tells that the previous state of the capacitor is the switch was closed. When the switch is closed, the voltage across the capacitor is 0.
0.
That means when you open it, then only it will charge.
Charge. Yes, sir. Sir, you told about self bias, na, sir?
Yeah.
Sir, what exactly that?
See, in our first problem, we have given 4 volt, no?
Yes, sir.
Then it is not self bias. That means we are externally giving a voltage.
Yes,
self bias tells that if you connect a voltage divider, then the same battery is used for all the transistors. See, you do one thing. That 5 transistor problem we have done, no?
Yes, sir.
In that first transistor, what did we connect? We connected some voltage, 3 volt something we connected. Do you remember?
Yes, sir.
Don't connect that 3 volt. Just put a voltage divider and see. All transistors will be on with that. Self bias.
Sir, in that case, we will reduce the DC power supply.
No. Only 1 volt, 1 battery should be used for all the transistors.
Yes, sir.
See, your cell phone is there. It has got millions of transistors in it.
Yes,
but
sir.
how many batteries you are using?
Single bat.
That means it is self bias only.
Okay, sir.
All the transistors in your cell phone are working with a single battery.
Okay, sir.
It is self-sufficient, self-equipped. It does not need an external voltage to bias a transistor. See, For single transistor itself, if I am using two batteries, 4 volt, 10 volt, how much foolish it is when our cell phone battery has got millions of transistors, but there is only one
Single
DC power supply for it.
Okay, sir. Sir,
Yeah.
I think 14F, sir. Sir, here we converting NPN to PNP, na, sir.
Yeah.
Sir, here collector is connected to plus 10 volt, na, sir, in NPN. But
Yeah,
your
collect. See, upper part should be plus, lower part should be minus.
minus. So, okay, sir.
Then only as you go up, voltages will be in increasing order. No, that is
Okay.
basic rule. If I down portion connect plus up minus means as you go up, what will be the network voltages?
Okay, sir.
Yes or no? So that
Sir.
means you please don't touch this part.
Okay, sir. DC, sir.
This part only this you have to change.
Okay, sir.
You
Sir,
see,
sir, another doubt, sir. Sir, you said we should not have VCC in our IC equation, na, sir.
yeah.
Sir, but you're putting in a op amp.
Yeah. Tomorrow I will remove VCC also.
Okay, sir.
Okay. That
Okay.
means in finally our equations will depend only on resistors, 1 or 2 resistors. VCC also tomorrow we are going to remove.
Sir, I really enjoyed this class, sir, today.
Thank you very much.
Thank you, sir.
Yes.
Hello.
Yeah.
Yes. Good evening, sir.
Yeah. Good evening.
So, why the load needs to be grounded? Means why we don't?
No, it's only a design option. See, suppose an electrical engineer is there, he wants to drive a DC motor. If I give him a amplifier circuit and ask him to connect a motor to VCC, then he will ask where is the ground node? Yes or no?
Yes, sir.
Load means one end should be grounded naturally. Any surge is there, high voltage. For him, it will be bypassed to ground. So similarly, when I'm designing an electronic circuit, I'm giving you two options. One is a floating load, the other one is a grounded load. If you want grounded load, then you have to connect a PNP transistor. Otherwise, what we have to do? Suppose somebody says, no, I want grounded load. Then you have to lose the voltage, no? See here, this is a transistor circuit. If you want grounded load, then what they can do? Again, one output capacitor they have to put and then connect to ground. So this is headache. Already your RC is load, no? But because it is floating, now we are removing it. We are connecting one more RL with an extra capacitor here. So this is nonsense. So if you want a load which is grounded, go for a PNP transistor at last stage.
So one more doubt. In questions, we were like checking in op-amp question. We were checking V1 is greater than V2. Then it is negative feedback.
Yes.
No, I said the opposite. When V1 is less than
V1 is
then
greater than V2, then VOP is
Positive.
on. VOP
Yes,
is
sir.
positive. V2 is
Yes,
greater
sir.
than V1, VOP negative. Yeah, you are
Yes,
right.
and negative feedback. Then, if there is a negative feedback, then we have studied that V1 will be equal to V2.
Yes, finally, once that comparison is done, and if there is a negative feedback, then definitely within no time, there is a continuous comparison and virtual ground is set up.
Okay, means when we conclude that feedback is negative, then we can apply
When
that.
you conclude that there is a loop, through that diode or through that BJT, then there is a negative feedback. Then you can apply virtual ground.
So we can apply virtual ground in diode and BJT.
Yeah, we provide diode. Yes, you can apply. No, suppose op amp is there. We have connected a diode here. We have connected a diode here. If the diode is on, there is negative feedback. No.
Okay, I did that. Okay, sir. Yes, sir. One more doubt that the capacitor. Sometime when AC source is there, sometimes we take capacitor as short circuit, but sometimes we charge it to VM.
Yeah. See, when capacitor is there is no charge in the capacitor. That means its voltage is zero, no?
Yes, sir.
Voltage 0 means short circuit.
Yes.
Capacitor is fully charged. Fully charged. When a capacitor is fully charged, its current is 0. Current 0 means open circuit. These are the
Yes,
two
sir.
models for capacitor. This will
Yes.
happen initial, when a capacitor is charging. This will happen finally. The same example, you can imagine your cell phone. Your cell phone battery is completely drained. You want to charge it. How will you charge your cell phone? The moment you plug in, the voltage across your cell phone is still 0. It cannot change suddenly. Slowly, first point, second point, third point, fourth point will come. So initially the voltage is 0. Your cell phone is acting like a short there, the charger. But if once your cell phone is fully charged, it will not take any more current. Suppose you forgot, you have connected the cell phone to a charger, and next day you are seeing it. It would have charged in the night itself. Yes or no? The current is 0. Current 0 means open circuit.
So this I understood. Like in last class, we did one question where AC and DC both biasing was there, and when we
That is
were
superposition theorem.
yes, sir, that's okay. When we done DC, then we opened
Yeah,
the capacitor.
DC means frequency is 0.
Yes, sir, that I understood. That open circuit one
Frequency
I
0 means
understood.
1 by 2 pi FC is the impedance offered by capacitor.
Yes, sir, that
For
will be
frequency
infinity.
0, it is infinite, no? That
Yes,
is why
sir,
it is
yes.
open circuit.
Yes, sir, that. So, and when AC source is given, then we are considering short.
Short. F is high. Mid frequency range and F is high. 1 by 2 pi FC. This is very low. Low means short.
So, in every case, when AC signal is given, then we
Yes.
have to take that it will be short or it will be get charged to VM.
No. Charge to VM is when you have a diode in series to a capacitor. That means the charging is here like this. Till here the diode is on, no? After that the diode is off for the next 100 years. In only this kind of a scenario it will charge to VM.
Okay.
Suppose you are given capacitor, resistor input. Why you have to take VM? You cannot take VM. It will charge like this, discharge like this, charge like this, discharge like this, charge like this, discharge like this. When you give a sine wave to a capacitor RC network, it will charge and discharge. No, it will allow. It will allow all frequencies till F equal to 1 by 2 pi RC. All sine waves will come.
Yes, sir, yes, I understand.
If you put a diode, then the diode will not allow current in the opposite. But whereas capacitor, what is the benefit if you have a capacitor? Like this current will flow for positive, like this for negative, like this for positive, like this for negative. But if you have a diode and a capacitor, finish. The diode will allow current only in one direction. Opposite, it will not allow. Then it will charge to VM.
So one last doubt, like in edge of saturation, that EC should be equal to EB till then, and after that there will be difference which will be given to IC should be IB, and after
After that, if you beyond that point, if you increase the resistor, extra current will keep on sinking through base region.
yes, sir, yes.
IB current will increase beyond that.
Okay, sir. Thank you, sir.
Okay. Can you just wait for 10 seconds? I will bring water.
Okay, sir.
Yeah, I'm little thirsty. I'll just go bring water. Just Yeah. Next. Any more doubts?
Hello,
Yes.
sir. Am I audible?
Yeah.
Yeah, sir. Sir, actually, I have a simple doubt. So actually,
Yeah.
you compared at some instance diode with op-amp. Sorry, transistor with op-amp circuit.
Huh.
So, sir, can you give me the part where you have compared? Can you give me the
Yeah. I
parts
was yesterday before starting BJT, I was telling that a diode dynamics, if you see, if I give a millivolt signal, I'm getting microampere current.
Okay.
But in BJT, if you give a millivolt signal at the input, your base current will be micro, but your collector current will be beta times of base current. That will be milli. But when that milli flows into kilo ohms, you get volts. So if my input is in millivolt, my output will be in volts in BJT.
Okay. Sir,
That
sir,
option
can you
is
repeat
not
what
there in a
you told
diode.
about diode?
Diode only microampere of current will flow. What is there? If you allow it to flow through a resistor, some millivolt drop.
Okay. And sir, one thing, you compared BJT with op-amp.
I compared
in today's
BJT with
class, sir, can
op-amp.
you explain that? That is I'm not.
Did I compare BJT with op-amp? Acha, in biasing.
I'm unclear at that point.
And at biasing,
Hello?
what did I tell is, two transistors with the same temperature coefficient you have to connect, no? This one, this circuit, yeah, this one I compared, no? Is this a circuit?
Okay.
Yeah, I told that
Yes, sir.
to bring back the same voltage, I have to have two transistors with the same temperature coefficient. That is expensive, I'm saying. Op-amp is a general purpose IC. These transistors are batch transistors.
Oh, yes, sir. Hello.
Yeah. Can you hear me?
Sir? Yes, sir. Yes.
Can
Hello?
you hear me?
I'm not getting you.
Can you hear my
Hello?
voice? Yeah.
Hello.
Yes, sir. It's audible. Sir.
Yeah.
Sir, I had a doubt in last session, sir. It's a very
Yeah.
small doubt. Sir, while checking the saturation region, sir, in PNP, there plus 0.2 and minus 0.2 had creating little bit confusion, sir. That means how to calculate VE and VC.
VCE calculation, huh? VC
Yeah,
minus
sir.
VE.
No, VE and VC calculation, sir.
Yesterday's yesterday
34F, sir. 34F, sir. Little small doubt, sir. Only.
Yeah, no problem. No doubt is small. Everything is important only.
Yes, sir.
Yeah, which page?
34F, sir.
Yeah, tell me.
Sir, here V and VC, sir, 0.7, 0.5.
Yeah.
Sir,
This
once
is
explain that,
here
sir.
you have a diode here, no? This is a diode.
Yeah, sir.
And here there is a 0.2 volt. This is 0 volt, ground. Am I right?
Oh, okay,
Now you don't know what is this voltage. You can take this as
Yeah.
X. Here there is a drop of how much? 0.7.
0.7 volts, yes. Sir.
So X minus 0. See the plus terminal, higher potential. Minus terminal, lower potential. X minus 0 is 0.7. What is X? X is also 0.7. Am I right?
Okay, sir.
X minus 0 is 0.7. That means your X is 0.7?
Yes, sir.
Yeah. Now, this is Y, this voltage. X minus Y is 0.2. X minus Y is 0.2. Are you getting?
Yes, sir.
Excuse me. X minus Y is 0.2. X is already 0.7. That means your y is 0.5.
Okay. Yes, sir.
Are you getting?
Sir, if there is this, yes, sir. If there
Yeah,
is a
simple.
6 volts,
I'll tell
then
you.
V is 6.7, VC is
V
6.5, na, sir? If there is a 6 volt at base terminal,
6
V is
volt at base
6.7.
terminal.
Yes, sir. V is 6.7 and VC is 6.5, na, sir?
This is 6 volt, 6.7. If you go up, what you'll do? You will add, no?
No, sir. I am asking PNP, sir. For PNP, it is NPN.
Aha, PNP you want, huh? Tell me PNP. This is 6.
Yeah, yeah.
If you go up, you have to add 6.7. This is 0.2, 6.5. Perfectly correct.
Okay, sir.
Perfect.
Okay. That difference should be 0.2 only, na, sir?
Yes, yes. Only in saturation, my dear.
Ah, yes, sir. Yes, sir.
Yeah, yeah, yeah.
Okay, sir. Thank you very much.
Okay.
Hello, sir.
Yes.
Sir, 13, page number 13, sir.
Page number 13. One three, yeah?
Yes, sir.
Yeah.
Sir, here in the below small diagram, sir, the drop is minus 1.4. No, sir?
Where is minus 1.4? Here.
Yes, sir. Two
No,
diodes.
this is ground, no? This is ground. This is parallel. In parallel connection, voltage is same, no? In series, it will add.
Okay.
For example,
yeah,
what you are saying is this. Two diodes are in series. This is 0. Here the drop is 0.7. Here also the drop is 0.7. Then this voltage X, 0 minus X is 0.7 plus 0.7. That means X is minus 1.4. Is this your doubt?
Okay, okay.
Yeah, yeah, yeah.
Like this is like two resistors connected in parallel, right? Sir?
Yeah, you're right. Only one value will be there.
Okay, okay, sir.
But the current will divide. If two resistors are in parallel, voltage is same. But what will happen to the
Yes,
current?
sir.
The current is going to get divided into half, no? If this
Yes.
is total I, this is going to be I by 2 and I by 2.
Yes, sir.
Like that, the diode current, I0, can you see I0 here? I0.
Yes, yes, sir.
Here it is I0 by 2 and I0 by 2.
Yes, sir.
So what is the summary of the discussion here? If two components are in parallel and if they experience same voltage, the current will divide but voltage will be same.
Same.
In series, what will happen? The voltages are added up, but the current is going to be same.
Same.
Yeah.
Yes, sir. Sir, 20F.
Yeah.
Sir, here you have took directly the equation how you took, sir, without KVL.
No, I substituted 2 in 1 only. But
No,
what
sir.
I want to tell is, there is, see, I'm giving some voltage 5 volt. Okay, I'll write it like this.
No, sir, like below you have directly written, sir, without applying KVL.
Yeah, that's what I'm telling. Suppose I'm having V here. Okay.
Yes, sir.
I'm having a transistor here and a resistor here. This is R. What did I tell you when I started this BJT lecture? If this is 4 volt, this is how much? 3.3, no? This is 1 milliampere. Are you getting?
Yes, sir. Yes, sir.
Yeah. So now, if this is V minus VB. Is it okay? And here there is R. So what is the current I? It is V minus VB by R. Is it okay now?
Yes, sir.
Now, in the same circuit, if I have, this is R1. If I have R2 here, then we are writing two equations and substituting. Instead, what I'm saying is, here what is the current? IB.
Yes, sir.
But IB, can I write it IE by beta plus 1?
Yes, sir. You can write.
So what is the voltage drop here? IE by beta plus 1 into R2.
Okay.
So if I imagine there is only one IE here, For that R2, I will divide by beta plus 1, I am saying. I will write the same KVL.
Okay. Only for R1 it is dividing. I thought whole is dividing.
Only for R2 we are dividing.
Yes.
For
yes.
base RB. So where is that slide? Can you tell me the page number?
20.
20F. I'll show you once again. Then you will get convinced. See, RTH is the base resistance. Am I right?
Yes,
So
sir.
what did I do? V minus VB by RE plus RTH by beta plus 1. That's all.
Okay.
Are you getting?
Yes, sir.
Yeah. Already, see, V4 minus 0.7 by 3.3 we have already done, no?
Yes, sir.
Extra one resistor has come. We'll divide it by 1 plus beta. What is that?
Okay. KVL only we are applying directly. Like.
Okay. By seeing that circuit, I'm directly applying. But
Yes, sir.
otherwise, substitute 2 in 1. You will get.
Yes, sir. We will get in that.
2 in 1, you substitute. 2 equations are there. Second equation is IB is IE by beta plus 1. You substitute there in the first equation. You will get the same thing. No?
Yes, sir.
Yeah.
And sir, one more that ISC problem, sir. That what is the device, sir, which it is connected, sir? Actually, I am seeing that first time that kind of questions.
Which one?
ISC Bangalore.
The last problem we have done, no? This one?
No, sir. 150 ohm between.
Yeah, this one only. No?
This one. This is actually that is not resistor, sir.
Acha, this one, this is a potentiometer. You can vary. Suppose if your arrow is here, what is the voltage? 0. If your arrow is here, it will be 1. It will 2, 3, 4, 5 like that. It is a potentiometer, no? You are tapping.
Okay.
Or you can do one thing. You can imagine this resistor as 5 resistors of 1K each. 1K, 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 1K. Now tell me, here, if I connect it here, it will be 1 volt, no? Connect it here, 2 volt. Connect it here, 3 volt. Connect it here, 4 volt. Connect it here, 5 volt.
5 volts.
Direct supply. Can you see?
Yes, sir.
Yeah, it is a potentiometer. That's all. It is varying from 0 to 5.
Okay, sir.
Yeah, that means input range is from 0 to 5.
Okay, sir. And here in this question, VOP and VB are in the same potential, right, sir?
No, drop is there, no 150 ohms drop.
So I need to take.
If 150 is not there, 150 ohms is not there, then your VOP and base terminal both are same.
Okay, like VB minus VOP I should take, or VOP minus VB, sir?
VOP minus VB, not VB. This voltage is VB.
That only, sir.
This is VE.
I should take VOP minus VB equal to 150, or VB minus VOP equal to 150?
VOP minus, because IB is this current, no?
Okay, as op-amp has no current.
Current always flows from higher potential to lower potential. So if you have 2 resistors now, V1, V2, R and IB. IB is V1 minus V2 by R. Or you can do one thing. You can apply KVL also if you want. Suppose, see, if I can understand your mind is saying, how that loop is going to see here. This is a transistor here, no?
Yes, sir.
Here, how much voltage? Minus 15. This is IE.
Yes,
This is 10 ohms. This is IB. And here there is a voltage VOP. Voltage at any point is a voltage at that point with respect to ground.
Yes, sir.
So your VOP is this. You can take a loop like this.
Okay.
Minus VOP plus IB into 150 plus this voltage 0.7 plus IE into 10 minus 15 you can take.
Okay, sir.
Or if you want this VB, then you can draw like this. Voltage at any point is a voltage at that point with respect to ground, no? So you want VB. That means this is VB only. This loop you can take.
Yes.
Remember, any voltage at a point is with respect to ground.
Okay, okay, sir. Got it, sir.
Yeah.
Sir, one general doubt I'm having, sir, like nowadays the mobiles will be there, right, sir, of 5000 mAh battery.
Ah.
So it is like a self-driven, sir. It is actually like small amount of voltage, or it is enough for transistors to activate the mobile?
No. It all depends on the power driving capability. Voltage will be same.
Okay, sir.
But the battery, it all depends on power. That means current. A load is always current driven, not voltage driven.
Okay.
Voltage is fixed, no?
Voltage fixed.
It's power. The power size increases, size of the battery. Some cell phones are light.
Yes,
Some
sir.
cell phones are heavy, if you can see. They will say that we can charge within half an hour.
Yes,
Voltage
sir.
is same. But
35 watt battery.
Yeah. The mAh, what they say, the power current driving capability is different.
Okay, sir.
Yeah.
Okay, sir. Thank you, sir.
Okay.
Hello, sir. Can you hear me?
Yes.
Sir, you just mentioned that when DC voltage is applied to a capacitor, the capacitor acts as an open circuit, and hence the current across the capacitor should be 0.
Yeah, once it is fully charged.
No, sir. Right after DC voltage is given to the capacitor.
Yeah, I mean, like, it all depends on the time constant. No, you have to wait for some time. Once it is fully charged, final value, current is 0, voltage is its open circuited voltage.
So after we connect the DC voltage at T plus, wouldn't it be open circuit, sir?
No, it will be short circuit because the current is maximum.
Sir, but it is a DC voltage, sir. Now open page number 6F, sir.
Okay, let me draw here. For example, if I have 5 volt with 1 kilo ohm, there is a switch capacitor.
Okay, sir.
Once you close this T equal to 0, at T equal to 0, this capacitor VC is at 0 for T equal to 0. For T equal to T1, it might charge to 1 volt.
Sir, at T is equal to 0 plus, what would you say, sir?
The voltage is 0. The current is maximum. I at 0 is going to be 5 by 1K maximum.
But we usually take, when we were doing the filters, the analysis, when we said omega is equal to 0, the capacitor is open circuit.
That means what? Just see, very good. Your doubt is, here if you wait for T equal to infinite, no? That is the steady state value, 5 volt. That is open circuit. You are right. That from here to here, it is hardly like 1 or 2 milliseconds. This you have to wait in filters. In filters, once you switch on, wait for some time. We should have patience till that circuit will go to a state called steady state. That is where they are steady state analysis.
Okay, sir. So we can't say when a DC voltage is given, the capacitor is open circuit.
Yeah, it is open circuited. That means what? It will fully charge. See, it is open circuit means what? It is not taking current, no?
So it is open circuit at T is equal to infinity. But at T is equal to 0 plus,
T equal to infinity after it is fully charged. That is what we say capacitor blocks DC.
Okay, sir.
What do you mean by block DC? It will have its complete voltage across it.
Yes, sir. Okay.
See, one simple example I will give you. Suppose I am having a transistor, here 6 volts is there. There is another transistor where the voltage at this point is 3 volt. Now you show me a device, or 2 volt. You show me a device which will say that 6 volts I am blocking you here. 2 volts you stay here. Don't go anywhere. 6 volts, 2 volts stay. If you connect a capacitor here, you know what will happen? This capacitor will charge to the potential difference. 6 minus 2 is 4. As long as there is 4, this fellow will say I am 6 here, I am 2 here. Capacitor will only charge to the potential difference.
Okay.
Okay. And that's how the current becomes 0 here. DC current.
Okay.
Capacitor will block DC. That means whatever is there, when you open the capacitor, whatever the voltage is there, after you connect the capacitor, same voltage will be there. See here, suppose this is 10 volt, 5K. If you connect a capacitor, tell me how much voltage will it charge?
You should have 10 volts.
No, 5 volt. Open circuited voltage.
Okay. Yeah.
You should open and see how much voltage is there. That much voltage only it will charge. So it will block this voltage across this. Blocking means nicely eating and charging. See, it's something like when we will say we don't want food after we have eaten full, no?
Yes, sir.
So capacitor, if he says I don't want, I want to block this, that means that DC is across him only. He is fully charged. Don't believe if somebody says capacitor is open.
Yes, sir.
In open circuit means he's fully charged. He's not taking current.
Yes, sir. That I understand, sir. So here, when you connected these two BJTs, so consider if there's a switch over there.
Where there is a switch?
Right after 6 volt.
Right after 6 volts, there is a switch. Yeah, very good.
So after you.
The moment you close it,
Yes,
the
sir.
moment you close it, there is a 6, there is 2. If
So
there is
there-
a resistor, 6 minus 2 by R of the current will flow.
Okay, sir. Okay, I understood, sir.
Yeah. And after, in final state, it will be 4.
Okay, sir. But when we're doing the filters, we consider at omega is
state.
equal to 0.
Filter analysis or sinusoidal analysis is steady state analysis. That means you should wait
Yeah,
for
understood.
some time.
Yeah.
You should have patience. Once you switch on, have a cup of coffee. Let all the circuit elements go to a state called steady state.
Yes, sir. Understood.
Yeah.
Okay, sir. Yeah. Thank you.
Okay.
Hello, sir.
Yeah.
Sir, I didn't understand the concept of thermal stability and temperature
Which
coefficient.
one? Your voice is
Thermal
too low.
Sir, thermal stability and temperature coefficient. How that VB and all is eliminated.
Thermal stability means, see, if temperature increases, suppose the current IC is increasing, and again with IC increase, there will be increase in temperature, there will be IC increase. This is called a runaway problem.
Okay.
Runaway problem. So if you want IC to be constant, in that loop, IC should decrease, the increase should decrease. So that will come only in negative feedback. In negative feedback, what we are doing in negative feedback? In negative feedback, there will be something like this scenario. In negative feedback. So if your output IC is increasing here, then automatically here ICRE will also increase, or IERE will increase. This is your VB. What happens if IERE increases? Your VB will decrease. This is your VBB. So VB equal to VBB minus IERE, negative feedback. So tell me, if IERE increases, your VB is going to decrease, no? This VB less. If VB is less, then your IC is IS into e power VB by VT. If VB decreases, your IC will decrease. Can you see?
Yes, sir. That
First I started with IC increase, then I came with IC decrease. If IC decreases, IERE will decrease. Your VB will increase. And then your IC will increase. So this effect is called negative feedback effect. The same effect you will get with circuits here. Can you see?
Yes, sir.
So if temperature increase, IE will increase, IERE will increase, VB will decrease. If VB decreases, IC will decrease. Finished.
Okay, sir.
Are you getting?
Yes, sir.
Yeah.
Hello, sir.
Yes.
6F page number.
6F.
Next page. Sir, in that when we calculating the saturation, 1 plus 0.2.
Yeah.
Sir, 0.2 1 where they say
How I have added it, you want to know?
Yes, sir.
No, simple. This is, you can take this as X. You can take this as Y. X minus Y is 0.2, no?
Yes, sir.
X minus Y is 0.2. Am I right?
Yes, sir.
Now, your Y is 1 volt. X minus 1 is 0.2. X equal to, if you take minus 1 to the other side, it will become plus 1. 1.2 you'll get.
Okay.
So that means if you go up, you have to add. That's all. 1 is there. I'm going up. What is this? 1 plus 0.2. Suppose I'm
So-
coming down.
Oh,
If suppose this voltage is 6 volts, this point is 6 volts. If I come down, 6 minus 0.2 will be this voltage. Are you getting?
yes, sir. For any saturation, we calculate a saturation plus VA, sir.
Yeah. This voltage VE plus 0.2. How much is this? 1.2 in saturation. So 10 minus 1.2, 8.8 volts the capacitor should charge. It will charge to 8.8 in 8.8 millisecond.
Okay, sir. In 30 FPS.
Yeah.
The second B question, sir.
Yes.
Sir, in this RC how you calculate? I'm not understanding. 4 volts equal to
Yeah, this voltage is 4, no?
IC voltage.
VE is 4. Is it okay now? Because this is 4.
Okay, sir.
4, 4. 4 minus 0.2, this is 3.8.
3.8. Okay.
Okay. What is 3.8 by 2 milli?
1.9.
1.9.
Sir, in next question, 32F. VE taken when diode not minus, no, sir.
What?
I'm sorry.
Tell me.
V equal to 2 volts only.
Yes, VE2 equal to VC1. VE1 is 2. This VE1 is 2.
In previous problems, sir, we take VE means voltage minus 0.7 diode voltage.
This 0.2 is VE minus VC, no? This 0.2 here is VE minus VC, difference. This is voltage with respect to ground.
Okay, sir.
This VE2 is with respect to ground. It is this drop minus 3.
Okay, sir.
Yeah.
Hello, sir.
Yes.
Sir, could you explain once the difference between the EOS and the saturation, sir?
EOS and saturation.
Yes, sir. And when the EOS is given, how do we solve the problem? And when we want to know the saturation region, how do we solve like that?
See, EOS problem, resistor we are finding, that's all. Are you getting? Resistor.
Yes, sir.
Suppose saturation means everything is already given to you. Suppose this is 1K and the transistor, suppose here I have given 4 volt. This is 3.3K. What you will do, this is 3.3 volts. 3.3 by 3.3, 1 milli. This is also 1 milli. We are calculating, that's all. For saturation, suppose instead of 1K, it is 10K. If it is 10K, then pakka it will go to what region? Saturation. This 1 milli is wrong. So, how are we going to solve this problem? We have to take 0.2 here.
Yes, sir.
3.3 plus 0.2, 3.5.
3.5.
Now, this is IE. IE will be small
Sir,
because
that
of
is
10K.
3.5.
Sorry, this is IC, no?
Yes,
Here
sir.
IE. Now you will have a large IB. But we don't know when it went to saturation. For 1K, it was in active. For 10K, it is in what region? Saturation.
Saturation
Your
region.
EOS will be in the middle. Your EOS is going to be in the middle. Are you getting?
Yes.
How to find that EOS value? To know that EOS value, this 10K we have to remove and we have to put RC there. We have to put RC. This is 4 volt. This RC. I don't know what is RC. It is not 1K, it is 10K. Because 1K it is active, 10K it is in saturation. So again, I will repeat the problem. This is 3.3 volt, 3.3K. How much current will flow? 1 milli, na?
Yes.
Here also 1 milli for active, because this in this line you are here in active, here in saturation, no?
In between
So,
also active.
so same 1 milli will flow. This is 0.2. So here we have 10 volt. Now this is going to be 3.5. Now you tell me the value of RC. RC equal to 10 minus 3.5 by 1 milli.
Yes.
It is going to be 6.5K. So 6.5K is EOS. Are you getting?
Yes.
If it is less than 6.5K, where it will be active?
In active region.
If it is more than 6.5K, it will be in saturation. That's all. That is EOS.
Yes. Yes, sir.
Are you getting?
Yes, sir. I'm good.
Yeah, good.
Sir, and sir, the drift problem in this, how we are eliminating the drift problem? Can you explain, sir?
How will
By
those two
VBE
transistors we have
compensation.
connected, no?
Yeah. Yes, sir.
One is adding 0.7, other one is subtracting. That's all. Net effect is 0, no? If your IC is independent of VBE, then we have eliminated drift. Two
okay,
diodes
sir.
we have connected like this. One transistor is like this. Another transistor is like this. This is a PNP diode. This is an NPN.
Yes.
Here I am giving X. This will be X plus 0.7. Then this will be X plus 0.7 minus 0.7. It is X. One is adding 0.7. The other one is subtracting 0.7. Drift is gone, no? Because now our X is independent of 0.7.
Yes, sir.
Yes or no? Here we will connect an emitter resistor. So your emitter current is completely independent of 0.7 because 0.7 is getting cancelled. Minus 0.7 plus 0.7.
Okay, sir.
Are you getting?
Thank you, sir.
Then how do I
Yes,
get
sir.
this? You have to have a PNP and an NPN to get this. Okay?
Yes, sir. I got it, sir.
Yeah. Next.
Hello, sir.
Yes.
Sir, can you? I actually understood some half part, sir. 6F, sir. Can you please explain 1 second?
6F.
Yes, sir.
Yeah. Tell me, what is your doubt?
Sir, here in 6F, the arrow is outside, sir. That's why we are closing it, sir. Like we are making it short
Yeah,
circuit.
we are making it open. The arrow is outside, no?
In below diagram, you are making the current to flow in the short circuit direction, right, sir?
Yes, yes, yes.
Means at t is equal to 0 plus, it is short circuit.
Yeah. Here it is in the gate problem, it is open. This arrow indicates
Means
it is
the
open.
below
No?
diagram is.
This is below diagram.
Yes, sir.
This is general. For example sake, I have given. It is closed.
No, sir.
At t equal to 0 plus, it is closed. Yes.
No, sir. Below one more diagram you took that the direction, current direction.
Where is that diagram?
No. In that page only.
This
sir.
one, huh? Here.
No, sir. Below that.
This one,
yes, sir.
That
is t equal to 0 plus state, sir.
This one is t equal to 0 minus. The switch is closed now. T equal to 0 minus. T equal to 0 plus, it is open. like this.
Okay, it is open means capacitor is charged.
Yeah, it is charging.
Okay, in T equals 0 minus, capacitor is empty, sir. Like it
Complete,
has.
complete bypassed by the switch.
Okay, okay.
Yeah.
Thank you, sir.
Yes.
Hello.
Yes.
Sir, in the last problem, page
Ah.
number 35,
Yeah.
there below the load resistor, it is minus 15 volts, no, sir?
Below the load resistor.
In the diagram, minus 15.
Here.
No, sir, 35.
Ah.
In the diagram,
This diagram.
yes, sir.
10 ohms is there.
Below that, minus 15 volt.
This is minus 15 only. Yes.
Okay, in the next page, sir, 36.
Minus 15. Did I change the?
There, how
Yeah,
we
here I
got?
put minus 15 only, no?
Okay, sir.
Yeah.
VB value, how it is 2 plus 0.7, sir? 2.7.
No, VB is 0.7, no?
Yes.
Do you know VB is 0.7?
Yes, sir.
So if I have a transistor and this is 0.7 here, this voltage is VE, this is VB. So we have to write VBE equal to VB minus VE.
Minus VE.
VB is 0.7. VE is 2 volt. Am I right?
Okay.
So VB is, if the minus 2 goes this side, plus 2, 2.7.
Okay, okay, sir.
Or simply what we can say, at emitter 2, you go up. If you go up 0.7, you have to add.
Okay.
Yeah.
Thank you, sir.
Yes. Yes. Anybody else? Okay. We'll stop for today then. Thank you.